Good morning, everyone. So, like we did yesterday, I'm going to wait until I see some activity in the chat before I start properly, just to check that we're actually live. So if anybody watching can say hello in the chat, that would be great. Okay, looks like nobody is, but I think we are live though, so I'll just continue. So, good morning, everyone. I'm here with Sandro. Okay, here we go. There's some good mornings. So good morning, everyone. I'm here with Sandro Matarai. He is our first talker today. So he's a lecturer in the School of Maths and Physics, a senior lecturer in the School of Maths and Physics, and he teaches algebra in the first year, and Lie algebra if you go on to year 4. So he's going to talk about Platonic solids. Is that correct, Sandro?
That's correct.
Okay, good. But it's quite a long talk. It's pre-recorded and it's quite long. So it's going to push us right up to the end of the allocated time. So for this talk, I really do encourage you to ask your questions in the chat during the talk. And Sandro will perhaps try and answer some of the questions during the presentation. So in the interest of time, without further ado, I'll start the video now. Please enjoy, and we may have a little bit of time afterwards for questions as well. So just take me a second to find the video. Here we go. So enjoy.
Welcome to this lecture. My name is Sandro Matarai. I'm a senior lecturer at the University of Lincoln. And today I would like to present you a few facts about Platonic solids. If you Google Platonic solids, you will find loads of material, loads of information, starting with Wikipedia, and you can really get lost into it, maybe pleasantly lost if you like the topic. So I wish to select a couple or some bits of material which might be not so easy to locate, and I find particularly interesting about this. So let me switch to my presentation. So, well, you see Platonic solids everywhere, really. This in this picture isn't quite a Platonic solid. It's a kind of star. It's a Christmas star, a photograph which I took a couple of years ago. I had to cut out the images of some people, including children. So how does this relate to Platonic solid? Well, if you look at the tips, the corners of this star, there are 12 corners, and the positions of those corners match exactly the 12 corners or vertices of one of the 5 Platonic solids, which is the icosahedron. So in a way, this is an icosahedron in disguise. So just to remind you what we are going to talk about, these are the 5 Platonic solids, and the name suggests that these are known for a very long time, and these are the names. Each of the names refers to the number of faces. So these are three-dimensional analogues of the regular polygons in the plane, like an equilateral triangle or a square, and so on. So there is the tetrahedron, 4 faces. There is the hexahedron. Hexa stands for 6 faces. Obviously, this is more commonly called the cube. And there is the octahedron, 8 faces, and dodecahedron, 12 faces, and icosahedron, 20 faces. And the shape of the faces, well, all the faces are equal polygons with the same number of sides. And in some cases, there are equilateral triangles, specifically for the tetrahedron and the octahedron and the icosahedron. And in one case, they are squares, and in another case, they are regular pentagons. So these pictures and these will come up in another slide later on with a little bit more information on them. But this is just to remind you what the Platonic solids are. So the Platonic solids, well, they're also called regular solid. And this is one of many possible definitions. A regular solid is a convex polyhedron. So a polyhedron is something bounded by some 3D shape bounded by polygons, such that all its faces are regular polygons, each with the same number of sides. For example, in the case of the cube, you have 6 squares, so you are not mixing squares with other shapes like triangles. And the second condition is that the same number of faces meet at each of its vertices. So let me go back a second to the previous slide. Like in the tetrahedron, you see its triangles, and 3 triangles meet in each vertex. And the octahedron has also triangular faces, but you have 4 triangles meeting at each vertex. And in the icosahedron, you have 5 triangles meeting at each vertex. I also use the word convex, which, well, you technically need it, but I don't want to go into that at the moment. Essentially, it means that your shape doesn't have any inward going parts, like a glass, for example, you know. But I'm not going to explain it further. So, within the definition of a regular solid, there are 2 obvious numbers, 2 obvious parameters to name. They are traditionally called P and Q, for no special reason. P is the number of sides of each face. So in case of the cube, P will be 4, because the faces are squares. And Q is the number of faces which meet in each vertex. So in case of a cube, you have 3 squares meeting in any vertex. So Q will be equal to 3. And they are usually given together, these 2 symbols, these 2 parameters, in something called the Schläfli symbol. Schläfli was a Swiss mathematician. Now, these are local parameters. Local and global are 2 important words in many parts of mathematics. What does it mean? Well, if you look, the local parameters tell you what occurs around a particular point without looking at the whole object. So to tell how many, to tell P, you just need to look at one face. You don't need to look at anything else. And to tell what Q is, you just need to look at a vertex and count how many faces go into that, join into that vertex. Besides the local parameters, there are also important global parameters. F, E, and V. So now the meaning is more obvious of the letters. F is the number of faces, E is the number of edges, and V is the number of vertices. Faces are 2-dimensional, edges are just segments, so 1-dimensional, vertices are points, so they are 0-dimensional. And here's a list of, here's a table with all these parameters for the 5 Platonic solids. So, for example, for the tetrahedron, you have 4 faces and 4 vertices. And if you count the edges, you will see there are 6 edges. And the Schläfli symbol, or the 2 parameters P and Q, in this case are 3 and 3, meaning the faces are triangles, and 3 of them meet in each vertex. In the case of the cube, you have 6 faces, 8 vertices, and 12 edges. And the Schläfli symbol tells you each face is a square. That's what the 4 stands for. And the 3 faces meet in each vertex. And so on. Now, the last column tells you the number of symmetries. These are highly symmetric objects. And actually, that's partly one of the definitions, or better, maybe the most modern definition of regular solids is given in terms of how many symmetries they have. The symmetries, that means you can take a cube and rotate it and until it goes superposed to itself. So you can do rotation of 90 degrees, and you can do other rotations, and if you count all possible rotations, you get 24 rotations. So I will not use this last column in any further. So, but I would like to focus on this question: why are there exactly 5 regular solids? Of course, there are many cubes. Cube can be bigger or smaller, but that's all you can change. Now, there is a very easy argument, which is, well, if you want to follow the rules to build a regular solid, for example, if you use square faces, well, you cannot, how many faces can meet, how many square faces can meet in a vertex? Well, it must be more than 2, it must be at least 3, right? So, but it cannot be more than 3, because if you take 4 squares and join them in a common vertex, you get a flat thing, okay? Can lie flat on your table, and if you keep going that way, you're not going to build any bounded solid. So there is only one possibility to make a regular solid using square faces, and you have to put 3 in each vertex, and then you get the cube. And similarly, if you use pentagons, you get to the dodecahedron. But if you use triangles, then you have 3 possible ways, because you can join 3 triangles in each vertex, or 4, or 5, and there you stop. If you were attempting to join 6 triangles in each vertex, then again you would get a flat thing, because each internal angle of a equilateral triangle is of 60 degrees. So if you take 6 of them, you get 360, which means your 6 triangles will lie flat on your table, for example. And so this kind of argument tells you that, well, basically these are the possibilities. It's not quite complete and quite rigorous, but it's an easy argument. I want to focus and tell you a different argument, showing you that there are precisely 5 regular polygons or Platonic solids. which is kind of more important, and because it involves ideas which are much more general than this. So let me introduce some relations first between those 5 parameters. So the 5 parameters which we have seen, we have P, number of edges or vertices of each face, and Q, which is number of edges which meet in every vertex, or number of faces which meet in every vertex, which is the same. And capital F, the total number of faces, capital E, the total number of edges, capital V, the total number of vertices. There are 3 equations relating those 5 numbers. The first 2 equations come from counting the edges in terms of faces or vertices. So let me explain what I mean by this. If your solid has capital F faces, well, each face has exactly P edges. So if you multiply the number of faces times the number of edges for each face, you get a total of P times F edges. So it's like, well, you've counted all the edges. The problem with this argument is that you have counted each edge twice, because each edge has a face on one side and a face on the other side, and you have counted that edge for each of those faces, so you have counted it twice. So P times F is not the number of edges, but it equals twice the number of edges, so it equals 2 times E. And then you have another equation. You can do a similar argument with vertices instead of faces. So let's count the edges in terms of the vertices. Well, you know that in every vertex there meet exactly Q edges. So there are Q edges which go into every vertex. So if you take the number of vertices and multiply it by this Q, you are counting the edges. Well, not quite. You are counting the ends of the edges, but every edge has 2 ends. Every edge is a segment, and you've counted the ends of the segments. So what you have obtained, what we have found by multiplying V times Q, is twice the number of edges. Okay, so you have these 2 equality signs. So you have found 2 equations. Then there is a third equation, which I'm not attempting to explain this because this is a much deeper one. And this is called Euler's formula. Euler was a famous mathematician. So the formula is V minus E plus F equals 2. Okay, take it, trust me for the moment. I wish to show you how, using these equations, you may recover all of the 5 parameters in terms of just 2 of the parameters. Well, it makes sense. You have 5 parameters related by 3 equations, so each of the equations should allow you to get rid of one of the parameters, expressing it in terms of the other. So if you do it, if you do that, you should be able to express all 5 parameters in terms of 2 of them, and the 2 which we want are P and Q. So we want to express everything in terms of the local parameters. So we want to describe the whole regular solid in terms of what you see locally, looking just at a little bit of its surface. And I will show it to you on the next slide, but let me first point out that this kind of argument, which I'm going to show you, is much more general than the way I will present it to you. For example, it does not make any use of the fact that the faces are regular polygons. So it would still apply to solids whose faces are not regular polygons, as long as the two defining properties of a regular solid are satisfied, so that each face has the same number of sides, and in each vertex the same number of faces meet. Well, actually, you need something else. You need the polyhedron or the solid. You need it to be, as one says, homeomorphic to a sphere, which, well, if it made rubber, you can kind of stretch it and make it into a sphere. To see what this means, well, a different situation, you could make a strange solid which you can deform into what is called a torus, for example, something with a hole. A torus is the mathematical shape describing a donut, say, okay, with a hole through it. And then this Euler's formula would not work as it stands. You would have to put a 0 instead of 2 on the right hand side. So so this formula really belongs to a more general field than geometry. It belongs to topology. But then you can make it even more general. It belongs to graph theory, if you like. So a graph, very simply, is like the one you've seeing here in the picture. You have vertices, that is the red dots, joined by edges in a certain way, satisfying some basic rules. And this, which you see in the picture, represents the faces of the dodecahedron, the faces and the edges and the vertices. It's like, well, you take a dodecahedron, you remove one face, okay, so leaving a hole, and then if the thing were made of rubber, you could kind of stretch it out onto the plane and get a picture like that. So if you look at this, you see lots of pentagonal regions. You see 11 instead of rather than 12, but that's because the 12th region would be the what is outside the whole picture. Anyway, I don't want to say anything further about this, but just to tell you that this kind of argument is important because it is much more general than just the geometry of the Platonic solids. So let me go through the argument now. We want to use these three equations. I want to use these three equations relating the 5 quantities to show you why there are only 5 regular polyhedra. So our equations are P times F equals 2 times E, and then second equation 2 times E equals Q times V. And then the third equation was Euler's formula. So you may use the first 2 equations to find F and V in terms of P and Q, and then substitute into Euler's formula, and you find what is the equation which is written here. And then you do a simple calculation and you transform it into this new form. 1 over P plus 1 over Q equals 1/2 plus 1 over E. So you see we've gotten rid of F and V. You only have P, Q, and E, but now they must satisfy that particular equation. And now you look for solutions of that equation. And but P and Q and E are not just any numbers, any real numbers, for example. They must be positive integers. And actually P and Q must be at least 3. So in the end, it's not difficult to see that this equation has only those integer solutions with P and Q greater than or equal to 3 and E a positive integer. Why is that? Well, for example, if you take 1 over P, or if you take P and Q, P equals 3 and Q equals 3, you get 1/3 plus 1/3, which is 2/3, and then you can work out that E on the right hand side must be 6. Now, if you start increasing P and Q, or just one of them, you get to a point where 1 over P and 1 over Q become too small, and their sum of these two fractions, 1 over P and 1 over Q, becomes smaller than 1/2. But then if the left-hand side is smaller than 1/2, that means E is negative, and this cannot be. Okay, so this is the reason why you get only finitely many solutions, and you can just work out that these are exactly the 5 solutions, and they correspond to the 5 regular polyhedra as I listed in the overall table, which I showed on one of the early slides. Okay. Note that, so beware that this argument shows you the uniqueness of these, so shows you that there are at most 5 regular polyhedra rather than exactly 5. It does not show you that the 5 polyhedra exist. Okay, well, okay, I've shown you pictures, but you've seen many cubes, so you can be quite convinced that a cube can actually be built, but you've probably seen fewer dodecahedrons, and so you could possibly think, okay, let's start and build the dodecahedron. So I have 12 pentagons, or well, I have a number of regular pentagons made of cardboard, say, and let's start to match them together, glue them together along edges, and build this solid. And who can tell you that once you start building around the solid, somehow those faces don't match at the end when you want to complete it? Okay. Okay, so this thing made of pentagons may actually not exist in principle. Well, to make sure that it exists, you need some direct construction. Okay, I could show you a picture, but mathematically you need some kind of construction. Okay, I'm not going into that. Let's play around with Euler's formula and make a variation of the argument which I have just shown you. So let's take a football shape. So football, classical football, is made with X pentagonal shapes, faces, and Y hexagonal faces. So this thing is called a truncated icosahedron, if you want to know the name. But the question is, how many of each type of faces? So how many pentagons, X, and how many hexagons, Y, will form a football? Of course, you can just look at the picture or take an actual football and just count. Okay, that's the easy solution. But suppose you see only, I'm showing you only this side of the football, or maybe even less than the side, but I would like to work out how many pentagons and how many hexagons there are without seeing the whole thing. Let's see if mathematics can help us. So this is just a variation on the argument we've just done. So in this case, you don't have, not all faces have the same shape. You have pentagons, you have X pentagons, and 6 hexagons. So if I add together 5 times X and 6 times Y, I'm counting all the vertices. Okay, I'm counting 5 vertices for each pentagon, 6 vertices for each hexagon. Altogether, I get 5x plus 6y, but that's not the number of vertices. It's 3 times the number of vertices, because doing so, I have counted each vertex 3 times. Like, for example, in this case, where I'm showing with the pointer here, in case of this vertex, I have counted this vertex once for this yellow hexagon, and once more for this hexagon, and once more for this red pentagon. So I have counted it 3 times. So the equation is 5x plus 6y equals 3v. Then we can do a similar thing to count the edges. So again, 5 pentagons plus 6 hexagons. You have 5 edges for each pentagon and 6 edges for each hexagon. So the same number as before will now represent twice the number of edges. Well, this is similar to what we've done before. If I count, for example, this particular edge, which I'm pointing at with the pointer on the screen, I have counted it twice. Once as an edge, as a side of this hexagon on top, and once as a side of this hexagon below. So 5x plus 6y equals twice the number of edges. And then finally, if I want to count the faces, well, I have x pentagons plus y hexagons, add them together, x plus y equals f. Okay, so now I do something similar to what we've done before. We can work out v, e, and f from these equations in terms of x and y. And we can substitute what we get into Euler's formula, v minus e plus f equals 2. And this is what we have. This first thing here, first fraction is capital V, minus second fraction is capital E, and then this thing in parentheses is capital F, and the whole thing must equal 2. Now, let's just do the algebra. Simplification, well, I'm collecting the x, and then I'm collecting the y, and what happens at the end is that the y disappears. The coefficient of y is 0. So the letter y, the unknown y, disappears from my equation. I'm left with 1/6 of x equals 2. So, well, this means that x must be equal to 12. X is uniquely determined. And however, I get absolutely no information on y. So this is the conclusion. In such a solid, like the football, there must be exactly 12 pentagons. And we get no information about the number of hexagons. So in the particular case of the football, you probably all know that it has 20 hexagons. Okay, but this doesn't come out of this argument. What comes out of this argument is that, well, you could build a bigger football using perhaps more hexagons, but the number of pentagons must stay always the same. It must be 12. And here you can build infinitely many solids, as big as you like, made with pentagons and hexagon as faces. I'm stressing here possibly irregular. Well, if you take three hexagons, which are regular, each of them has an inner angle of 120 degrees. And so if you put them one next to each other, joining in one vertex, you will get something which is flat. So they will have to be irregular. I'm allowing here irregular faces. So you can join several pentagons and make a kind of curving surface. But sooner or later, if you want to close the thing into a ball shape thing, you have to add some pentagons. And mathematics tells you have to add exactly 12 pentagons. The thing on the picture on the right is a photograph I took from my office once. There was this dome. I don't remember what it was for. And if you look at that, the mathematics is very similar. Well, this is dome, so it's not a complete ball, but imagine you could complete it underneath, right? Make it into full solid. Then the faces would be triangles. You see triangular faces, and except that in some of the vertices, you have 6 triangles joining, like in this vertex or in this vertex. But in some other vertex, you have 5 triangles joining. And you can write down equations, and the mathematics is exactly the same as with what we have done in this slide or the previous one. Once you need to swap faces and vertices in the argument, but it is exactly the same calculation. And this calculation would tell you that the number of vertices, there must be exactly 12 vertices in this dome, assuming you completed it to a spherical thing. There must be exactly 12 vertices where 5 triangular faces meet rather than 6. Final application, again in some sort of playful way. Let's play another game with this formula, with Euler's formula. So the photograph, I recently took this photograph from a shop window. This is a nice shape made of, you see, pentagons and triangles. So this is made of X triangles. Let's call it X, the number of triangles, and let's call Y the number of pentagons. And then let's establish some rule, which you can see from here. In each vertex, like this one, you have exactly 4 faces joining. So 4 faces meeting in each vertex. Same would be with this vertex, same would be with this vertex, and so on. So the question is, the question is find X and find Y. So how many triangles and how many pentagons? Okay, so by this moment you will probably have counted the pentagons and the triangles from the picture, but let's stipulate that is not allowed. I'm not allowing you to count directly. Suppose you're looking at just a portion of this picture, and I'm telling you it keeps going in the same way all around, following the same rule. Can you work out X and Y from these rules? So let's see what we can do with Euler's formula and with a similar argument as we've done before. So now, so in this case, this is very similar to what we've done in the previous slide. You have X triangles. So if you count the vertices, you have 3 vertices for each triangle, so 3 times X. And then you have 5 vertices for each pentagon, so 5 times Y. If you add them together, well, you've counted the vertices, but you have counted each vertex 4 times. because in each vertex, like this one which I'm pointing at, you have 4 faces. So you have counted this vertex 4 times, and the same for every other vertex. So you get 4 times the number of vertices. Similarly, if you count the edges, okay, each of the X triangles has 3 sides. Each of the Y pentagons has 5 sides. Add them all together, you get twice the number of edges. Again, same argument as before. Each edge has 2 sides, one on one side and one on the other. And then X plus Y is the total number of faces. Then again, substitute into Euler's formula, and you get this equation. If you simplify the equation, it becomes X minus Y equals 8. So, well, we have a different situation from before. Y has not disappeared, but we found a relationship between X and Y. There must be 8 more triangular faces than the number of pentagonal faces. Well, we cannot proceed any further with this mathematics. So let's add another condition which we can see by looking at this locally, so at a little portion of this solid. Well, you see, adjacent to a pentagon, there are only triangles. So no 2 triangles are adjacent to each other. Okay, no 2 triangles share an edge, and similarly, no 2 pentagons share an edge. Or you can put it in other way. If you take any edge, you will have a pentagon on one side and a triangle on the other side. Well, then that means that if you consider all X triangles and count, and each triangle has 3 faces. Sorry, each triangle has 3 sides. So if you multiply 3 times X, you get precisely the number of edges, because each edge has precisely 1 triangle on one of the sides. And it also has precisely 1 pentagon on the other side. And so 5 times the number of pentagons, so 5 times Y equals E. So note the additional information that we have with respect to before. So we earlier knew that 3x plus 5y equals to E, and now we know separately 3x equals E and 5y equals E again. So we have this additional information given by this extra rule, which comes from the observation of a small portion of this solid. So if we put this new equation, well, it looks like 2 equality signs, but forget the E. The new equation is 3 times x equals 5 times y. If you put this equation relating x and y with the previous equation, x minus y equals 8, well, the 2 equations allow you to find x and y uniquely. So you find a unique solution, you can work it out, you find x equals 20 and y equals 12. So this thing has exactly 20 triangular faces and 12 pentagonal faces. And you can work that out without seeing the whole solid. That's the whole point of the argument, as long as you know the rule on how it keeps going when you go all around. And so this solid is called an icosydodecahedron. I could tell you more about this, but there is no time left. It is not a regular solid, so it's not one of the Platonic solids, because the faces are not equal. There are 2 types of faces, pentagons and triangles. So it belongs to a larger class of solids called Archimedean solids, which satisfy a weaker regularity condition than that of the Platonic solids. Okay, that's all for this lecture. I hope you enjoyed at least some bits of it. Thanks for watching it.
Thank you very much, Sandro. That was very good, really interesting. I remember that whatever it was outside of your office as well. I'm not sure what it was either. The big yellow thing.
Yes.
Some sort of theatre or something. I don't know.
Some sort of theatre, yeah.
So it doesn't seem there was any questions, but we do have a few minutes because I've checked the next interview with the student is quite short, so we do have a little bit of time for questions. If anyone wants to ask any now, but I was just going to ask if I go back to, I can find it quickly here. This table here. And maybe I missed you talking about this, but did you mention anything about this last column on the right? These rotational symmetries. Could you just maybe say a bit more about those?
Yes, yes. I said very little because I didn't want to go into that, but that's one of the interesting parts, aspects of these Platonic solids. So each of these solids you can has a lot of symmetries. We are considering only rotations. Say you can take your cube or your octahedron and then rotate it along around some axis until it gets into the same position. And as I mentioned that being regular, I gave one definition of being regular, but the better definition would be in terms of these symmetries, so being highly symmetric. And just one thing, for example, why do I have 24 symmetries in case of the cube, for example? Well, the 24 is exactly twice the number of edges. We have 12 edges. And what's the point? Well, if you focus on one edge of the cube, then you can, by a suitable rotation, bring that edge onto any other possible edge. Mm-hmm. But of course, you can do it in two ways because choosing one of the two orientations of the final edge. So that's a general rule. And well, those numbers are the number of elements of some groups of symmetries, and that would be a whole different.
Yeah. So we have some questions now from the chat. So there's one: would you ever find this knowledge of shapes being used in physics? So do you know of any applications in physics?
Well, I know that in the shapes of some molecules, for example, I don't know if it would be physics or chemistry, but you know, I'm pretty sure that there is molecules having where the atoms are arranged in certain ways, matching each of these. Then there is another area where not quite the Platonic solids, but this kind of regular arrangements of vertices are very important, which is crystallography, the structure of crystals. So these are usually not bounded things, but 3D shapes or 2D or 3D shapes which keep going with regular patterns. And that's an important part, application of not quite exactly this, but a similar sort of theory.
Yeah. So finally, just one quick question. So Ben says, that was brilliant. Thank you so much. I might have missed it, but is there a limit to how many shapes can be made with multiple types of regular faces?
No. Well, I don't think there is no limit. So I gave the example of a football, and you could insert more you could have a large number, any large as you like, of hexagons and put them together, and exactly 5 pentagons, and so you can build such a thing as big as you like. It's not that you can take any number, arbitrary number of hexagons. I'm sure there are some limitations, but as large as you like. Okay, so if you want to see in practical terms, you could have lots of hexagons and irregular hexagons and put them. You could place them on your desk next to each other, and you are building some flat thing which keeps going forever. Now, if your hexagons don't have necessarily to be regular, then this thing can sort of bend towards a solid. But the theory tells you need at some point to close your shape, you need exactly 5 pentagons. Or you could use triangles or something else, but if you want to use hexagons, it would not work.
Yeah.
You need, and if you the other possible shape which you allow is pentagons, you need exactly 12.
So if you can answer in about 30 seconds, does this have many links with other branches of mathematics?
Yeah, well, yes. Now the Platonic solids in themselves are a quite specific subject, if you like, but all the ideas which are around it, for example, Euler's formula or the groups of symmetries of them are present in basically all branches of mathematics. You could have symmetries of differential equations, for example, which are important.
Yeah, that's brilliant. Thank you very much, Sandro. So what we're going to do now is play a video of an interview with one of our alumni students, Jamie. That's about 7 minutes, and then we'll have our next talk after that. So thank you very much, Sandro. That was fantastic.
You're welcome.
So let me just find this video. Always takes me a second. Sorry, here we go. So, thanks, Andrew.
Hello, my name is Jamie Smith. I graduated from the BSc Mathematics program in 2018, and I'm now studying for my PhD whilst working as a mathematics and statistics advisor, but I'll talk about that towards the end. So I've always been interested in maths, science, STEM and law, and when deciding what degree I wanted to study, I wanted to pick something that would give me the most career opportunities in the future, which ruled out law, leaving me with maths, science, or just more generally STEM. In determining which STEM subject to pick, I was thinking what would be my preference. My preference would be something on the more traditional hard science side, so ruling out things like sociology or psychology. And I eventually settled on maths because I thought that would give me the most opportunities going forwards. This would also give me a larger variety in things that I would study, as opposed to doing something like, for example, zoology, where it would be one specific area. I thought maths would give me the most varied modules to pick from in my degree. So in looking at the most interesting parts of my degree, there are two clear standouts. Firstly, the maths pedagogy module, which I'm sure others will talk about in detail. And the second part would be the ongoing physics education. And for me, that was really important as part of the STEM subject that I was hoping to study. Often I find when talking to people about maths and, oh, I studied maths at university, they go, oh, well, isn't that just numbers? And whilst that is true in a lot of the cases, I was always interested in where does this apply in the real world? And the most obvious example of that is in physics. So in the first year, looking at things like Newtonian physics. In the second year, that would move on into more advanced physics in terms of mechanics, including Hamiltonian energies, for example. And then in the third year, moving all the way into fluid dynamics. For me, it was really good to look at these physics modules as it gave me an ongoing progress in the maths that I was studying. And also it dramatically increases employability, saying, yes, I got a maths degree, and I've also studied 6 or 7 physics modules. It really helps round off a person's academic experience. So I'm the first person in my family to go to university, also the first of my friends to go to university. So my expectations were probably quite far away from the truth when I first came. I was first expecting to be in an enormous lecture theatre setting for most of the academic events. I was preparing for lectures of 200, 300, even 400 people. And whilst it's true that lecture sizes have increased since I graduated, as I understand it, the largest is still first year calculus, and that's still at around about 100 students, still hundreds less than I was anticipating. I was also slightly concerned with the amount of support that I might receive. My expectation was that we'd receive very little. It would be a case of, here are your lectures, go, study, good luck. That's not the case. At the University of Lincoln in the School of Maths and Physics, there is a lot of support offered, both in terms of academic support through things like seminars and problem solving, and also the pastoral side. The pastoral side is what I was not expecting the most. When you go to university, wherever you choose to study, there will be a lot of support available to you, not just within your school, but also things like the student wellbeing, student support centres. There is a great deal of support. That's what I was not expecting. And in truth, that's what I was most nervous about before I came to university. My other expectation was that there would be senior academics, lecturers, senior lecturers, readers, professors who would be standing at the front of an enormous lecture theatre talking about complicated maths and physics and statistics. But I would never truly know who they were. Again, at the University of Lincoln School of Maths and Physics, that is not the case. You'll get the opportunity to meet all of the academics. In my many years at the school here, everyone that I've met, spoke to and studied with has been absolutely wonderful. The reason that this interview is not being delivered live is because I'm currently out working in Italy on a project which I've been doing for quite a few years now. That would not have been possible without the support of two academics in our school who gave up their own time to help me apply for this program and also teach me some basic Italian. So the academics in this school are incredibly supportive. It's one of the main reasons I stayed. So would I recommend studying at the University of Lincoln? Well, I chose to study here again. After completing my bachelor's degree, I chose to stay to do a master's by research in mathematics. So researching an area of maths in greater detail than you would normally get to on an undergraduate program. The area that I looked at is maths anxiety. So the psychological components of what inhibits students learning mathematics. And I think that shows a testament of how much I enjoyed it here. I chose to stay for an extra 2 years. And truly, even beyond that, I'm now doing my PhD at the University of Lincoln. Whilst my own area of expertise has moved away from maths and moved into education and psychology, admittedly the psychology of maths education, I'm still staying at the University of Lincoln. So did I enjoy my time here? Well, in total, I'll be here for about 10 years. And in terms of recommending the undergraduate program, I've been back to my old high school and recommended it in person many times. I think the program we have here is one of the best in the country. The student satisfaction speaks for itself. It's an amazing course delivered by amazing people. So what have I done since graduating? Well, as I mentioned, I stayed for 2 extra years to do my Masters by Research. I'm now staying for probably another 3 or 4 more to do my PhD in Educational Research. And in addition to the extra studying that I'm able to do, I'm employed as a Mathematics and Statistics Advisor. So I help undergraduate and postgraduate students with the maths and statistics required for their course. And that can range anywhere from foundation year nursing students with support for their functional skills maths exams, first, second year chemists and biology students, third year mathematics, fourth year computer science. And a lot of my job is supporting third year psychology students with the statistics they need for their dissertation. So the maths and physics and statistics that I learned on my degree program has now directly led to me getting a job in the area, particularly in the teaching education side of the area, my personal area of interest. And then in terms of the next few years, I'm hoping to finish my PhD, continue working as a maths and statistics help advisor, possibly doing some similar work in Italy or a different country for some more experience, and continue researching and presenting at conferences to help more students learn more maths. And none of that would have been possible if I didn't do my bachelor's degree in maths at the University of Lincoln. Ciao.
Okay. Thank you for that, Jamie, if you happen to be watching. We're a little bit behind schedule, but that's okay. I'm here now with Helen. Hi, Helen. Live from Greece.
Hi, Matt. How are you?
I'm fine. So you're going to talk about, well, you've recorded a presentation about
Yes.
models of prey and predators. So you teach at Lincoln, you teach linear algebra in the first year, and you teach
Yes, for
complex.
first years, I teach linear algebra that involves all students in maths and physics.
Mhm.
And in the second year, I teach complex analysis. That is for the maths students.
Yeah. So what we'll do is we will play your video. I think it's around half an hour, if I remember correctly. And then afterwards, we'll have hopefully plenty of time for questions.
Okay.
Okay, so let me just find the video. It always takes me a moment. Here we go. So enjoy, everybody, and please remember to put your questions in the chat on YouTube.
Hello everyone, my name is Helen Christodoulidis. I am a lecturer at the University of Lincoln in the School of Mathematics and Physics, and this talk is about giving you an idea of what is mathematical modeling. So to understand mathematical modeling, which in some sense is to describe a real-life system or a real-world problem by mathematical equations, to understand mathematical modeling, we give a simple example. So I have chosen one of the simplest examples of this type of models is called predator-prey models, and it is used to describe the evolution of two population species of two animals. So you see this little graph here, this X and Y. This will represent, as we'll see later, the populations of the two species. One is the predator and the other is the prey. And this type of systems that have only, for example, two variables, they can describe a complex system of nature, and this type of systems can go beyond and have vast applications. They can even describe epidemic models, as we will also going to see. Now, mathematical modeling is about finding the optimal way, so kind of to use the less possible variables to minimize the complexity of equations, and to fit as best as possible real data on the other hand. So minimizing complexity and maximizing how well they fit the real data. That is about mathematical modeling. And we're going to see this example of predator-prey systems. But before going to that, one comment is that when we have systems that evolve in time, the one way to what we are searching for to describe them is the rate of change of the variables, what is called the derivative of variables. So that is one of the key concepts of mathematics that are extremely useful here. And once we have found the equations, we have written down, then we apply our knowledge in mathematics and we try to understand them. We study them, and if we can solve them, we can solve them by hand, then we can have their full description. There are other cases when we have many variables and the systems are larger that we cannot predict analytically their solutions. In these cases, we use the computer and we simulate the equations of motion. But always we can have a qualitative behavior of how the system will evolve in time. Now, a comment before we go to the predator-prey system is that when we say about mathematical modeling, it's not only about systems that evolve in time. It is also about static structures in nature. We apply mathematics to efficiently describe what do we see: hidden patterns, symmetries, and self-similarity. So we use mathematics and we use formulas for efficiently describing a pattern that appears in nature. So how do we start? Suppose we want to model an ecosystem. We want to model how the populations of some species of animals change in time, and we want to express them with mathematics. We want to be able to predict how their populations will change in the future of the species, or for each of the species, and if it is a balanced or not ecosystem. So, first question is, how many species do we want to study? Here we see two variables, x and y. Suppose that, for example, x is the population of one species and y is the population of the second species. These populations might interact in the following way. X can be the population of rabbits, so it is the prey of the second species, that is the population of the foxes, that is y, and the foxes eat the rabbits, are predators, and the rabbits are their prey. That blue arrow here, so they kind of linked with this line segment, shows the interaction between the species, and it points towards the population of the predator. We might have more than two species. We might have three interacting populations. For example, plants, the rabbits, and Z is the population of the foxes. How do they interact? The first line segment has a direction, shows who is the predator of the plants, the rabbits, and the rabbits, on the other hand, are eaten by the foxes. So we have this arrow pointing towards Z. So here we have three populations linked in this way. We could have four interacting populations, and we could close that graph. Once we have fixed our variables and we know what we're going to study, the next step is to know how exactly our populations interact. What are the links between the species? This graph can be one choice, but it's not a unique choice. When we have four interacting populations, there can be many other choices. In fact, the number of choices is equal to the number of possible graphs. We can connect in a different way the variables to get different models. For example, here we have three predators and just one prey. X, W, and Z now represent the populations of three species that are all of the three of them are predators, and their food are rabbits, for example. So we could have two preys and two predators, or we could have like now three predators and one prey, or we could have three preys and one predator. So think at this moment, how many graphs can you create with four interacting species? The next step is to model with mathematics these interactions and these variables, how do they change in time. So each one of the variables is a function of time, and when it is a function of time and changes in time, it defines a rate of change, and that rate of change is the key to model systems that evolve in time. Mathematically speaking, what we need is the derivative for each of those variables. For simplicity, let's think that we have only two interacting populations, like here, the rabbits and the foxes. So we want to write the equations that dictate their evolution in time. We want to write down the derivatives of these variables. Now, step by step, the reasoning is the following. These are two interacting populations, but let's think for a while. How would they do if they were on their own? So let's put here a barrier separating the two populations. The rabbits would populate and populate because they have no predators around, their population would go up and up and up. Instead, the foxes would tend to extinct. Having no food will make them starve, and eventually they would die out. Now, if we remove the barrier and we allow these populations to interact, the foxes would eat the rabbits and their population would go up. Foxes benefit when being around rabbits, and the opposite holds for rabbits, who see their population going down. But when the foxes are too many, they don't have enough food, so they starve, and that causes their population to go down again. While the foxes are few, the rabbits found the chance to populate again and become more and more. So in principle, this ecosystem finds a very good balance between the two interacting populations. We want to write down the equations that determine their change. If they were isolated, the rate of change of the variable x would be something positive. That turns out to be proportional to the total population of the rabbits. On the other hand, the rate of change of the foxes is something negative. And the foxes starve without being around the rabbits. We have expressed their rates of change in time. We have found what is called the derivatives of these two variables. Now the big question is, when removing the barrier, what happens to these equations? How can we combine them? We want a link between the two equations. We want to add a term that depends on x and y. To link the variables, we can add something, a function that depends on both x and y. When foxes are around, the first equation should have some term that is negative. X and y are both positive, and minus xy is something that subtracts from the population of the rabbits, a negative term which decreases their population. What we subtract here will be added to the second one, to the population of the foxes. And that term is what actually links the two populations. It is a simple model that contains two variables, has minimal complexity, and it is the optimal way to describe the evolution of these two variables. And that is one part of mathematical modeling, describing with mathematics, with equation, in the easiest way, the optimal way, a system that in principle, this real life problem is very complex. And that is the elegance of mathematics. So the 3 steps in mathematical modeling is finding the variables, how many are they, what do they describe. Then second step is, if the system evolves in time, find the derivatives of the variables and write the equation that describes the dynamics of a system. The third step is to analyze the equation and perform a study that can be by reasoning in mathematics and writing explicitly solutions if that is possible, or by using the computer and simulating these equations, or doing both. One part that is analytically and treating a problem with a pen and a paper, or by programming in a computer, simulating the model and analyzing the outputs. Now in particular, this system can be treated analytically because it is a quite simple model. Of course, when we go to many variables and to higher complexity, the computer is more necessary. So we will give different examples where we will consider different parameters and see how changing the parameters affects the system. So what kind of solutions do we get? Now here we have chosen these equations here. You can see that in front of x, the constant in front is 1, and in front of y, in the equation below, the constant is minus 1. The solution of this system is the following shown in the graph here. You can see that the population of the rabbits goes up and down, like a periodic function, and the population of the foxes does exactly the same, just with a little shift in time. Okay, the two populations have the same maxima and the same minima. This ecosystem seems to be in a perfect balance. Let's change now the parameters. Now let's consider that the parameter in front of y in the second equation is minus 2, which means that the foxes tend to die faster. Then we get these solutions here. The rabbits with blue have higher peaks, and the foxes have lower peaks. Despite that, we have considered that the foxes now tend to extinct at a faster rate. The system is again in a very good balance. Just that the peak of the population of the foxes is half approximately of the peak of the population of the rabbits. Let's consider now that the rabbits populate twice faster as before, so that we have that 2 in front of x in this first equation. The coefficient now is double than before, and let's make the foxes have this minus 1/2 in front of y in the second equation, which means that their death rate now is much slower than before. So let's see if now this ecosystem finds a balance, and if yes, what kind of balance it finds. Since the foxes have a much lower death rate compared to all the other solutions, you can see that with the purple, their peaks in populations are now much higher compared to the peaks of the rabbits. However, the population of the foxes reaches very low values as well, so it has very low minima compared to previous cases, and moreover, the rabbits tend to extinct. The values of the blue lines nearly reach 0, which means that the population of rabbits is about to extinct. Although, because the population of the foxes reaches very low values, the rabbits find the strength to go up again and populate and survive. So that is, again, a balanced ecosystem, although both species are at risk, which means that if we slightly perturb this system by some, for example, external threat, the populations most probably will both extinct. So there are values of the system which make it very stable, that under external threats will go on in time and will everybody will survive. But there are other values of the system that put the system at risk. And of course, one can go beyond and model the external threats by adding some further terms in the equations. And then one can study numerically or by theoretical reasoning and analytically deriving solutions, how can we make a system more stable, and how much we are at risk, evaluate the risk that we are, and draw conclusions how to avoid such risks. Now, from predator-prey systems, I will make a big jump, and we stick to these equations, but we will change the scenario. Now, my x and y variables will represent something else. We will use them to describe an epidemic model that surprisingly has the same structure mathematically. So let's consider that a is equal to 0. Let's get rid of that term, which means that we have no birth at all in the x variable. The equation of the y variable is the same as before. Now we have added one more parameter, that is this epsilon, that is very small and is in front of the term xy, that is included in both equations, and as we have said, represents the interactions between two populations. And we consider that this is something very small. Now, why we're saying all this? Because we will try to understand what will be the evolution of x and y in time just by looking at the equations, which also shows how useful are the derivatives in predicting the future of a system. In epidemic models, this x variable will be the people that have not been yet infected by some infectious disease, and they can be infected. They have the potential to be infected. Y will be the population that is infected at the time t. The derivative of x is negative because it has that term minus epsilon xy. And since it is negative, it means that if we start by this blue dot on the axis, on the vertical axis, then that variable will be some curve that goes downwards and tends to vanish. It cannot increase because this derivative of the x variable is negative and can only decrease. The derivative of y, on the other hand, is a little bit of unknown. That derivative we want to determine whether it is positive or not. If it is positive, the purple curve will go up. If it is negative, it will go down. Suppose that this term initially is positive. It means that the purple curve increases in time. But this minus b plus epsilon x, there is always a competition between the variables and the constants. Epsilon is really small and x is going down in time. It decreases in time. So at some point, that term is expected to vanish. And after it vanishes, it will become negative. The derivative being negative means that eventually y will also vanish. So that yields this purple curve. So just by analyzing a bit the derivative, we can have a qualitative estimate of how the system will evolve in time. So without knowing anything about these equations and how we can solve them, we can have a qualitative prediction of what will happen in time. So even though we haven't solved the system, we can have a feeling, we can have an intuition how the system will evolve in time. The infected population will reach its peak, the maximum, when the derivative is equal to 0. So exactly when we have that x naught is equal to the fraction b over epsilon. Now, you will see some graphs that are produced by using the computer. Now, these curves, quantitative, take this shape here. And as we decrease and decrease epsilon, that interaction term, it means that we decrease the interaction between the infected population and the population that has not been infected yet. Now, decreasing further epsilon, which means that we decrease the interactions between these two populations, we get another curve for y that has a lower peak now. And the blue curve, the people that haven't been infected yet, tends a bit slower than before to 0. And what happens if we consider epsilon even smaller? We get this type of curves. The purple curve has a much lower peak and it never actually intersects the blue curve. That means that its values, the y values, are always lower than the blue values. Actually, there is a part of the population that have never been infected and they will never become infected because the infected population stabilized. So to conclude, this predator-prey type of systems can find a lot of applications in many different real-life problems, from ecosystems to epidemics and many other more. I hope you enjoyed this talk on mathematical modeling. What would be my last remark is that we were able to describe ecosystems and epidemic systems, that these are large systems and complex systems in principle, and by using only two variables, we are able to give a very efficient mathematical description of the problem by using models that are based on very simple assumptions. So thank you very much for attending my talk.
Thank you, Helen. That was great. Really good.
Thank you. It's a pleasure.
So there's no questions yet, but they tend to come in kind of as we go. So I guess I'll start off just by asking how realistic are these models?
That's a very nice question. So how realistic is this model? On one hand, we can say that it's not extremely realistic. It's not too realistic. Actually, this kind of models, they are kind of simplified, as I explained in the talk, because they involve very few variables and essentially very few parameters. I could say, for example, the rabbits we consider have a limitless appetite, for example. That's not something realistic, or that they find infinite resources, so they their population exponentially grows in time. That is, of course, not true. The more parameters we add to the model, then the model becomes more and more realistic.
Yep. Okay.
Maybe I could give a remark I didn't say in the talk, is that
Okay.
there are also computational models that do not involve equations at all. So they are equation-free, let's say. And these computational models are also part of mathematical modeling, just that they are equation-free. So we have to simulate it is just an algorithm simulated in a computer, and we have to look at the data to have an understanding of the model. While here we have an understanding.
Okay, that's a slightly different approach, yeah. So there's a question from Thomas Goodwin, which is actually kind of the question I was thinking of asking. This is a really good question. Can this kind of modeling be applied to economics?
Yes, they are applied in economics, and in the banking system, for example, the bank can model with this predator-prey equations the loan and the deposit. The deposit acts as the prey, and the loan acts as the predator. So based on these variables, the bank searches for stable solutions, of course, that benefit everybody, and they can estimate the interest rates, for example. But it has also further applications in economy.
I lost you. Where are you?
That
There we are. I'm back. Sorry, I was looking at a different screen then. Yeah, that's a good question. So any other kind of applications? So in physics, for example, can you think of any?
In physics, if we can find models that the equations are in the predator-prey style.
Because I think I spoke to you about this before, right? I kind of suggested that maybe and I don't know if anyone watching will have seen this before, the laser rate equations, right?
The lasers, they are not this type of models. I think they have X squares and Y squares.
Yeah, but I think they're kind of similar in some ways, but I don't think they quite fit. I don't think they quite fit.
They might look more like oscillating systems.
Yeah. Okay, so yeah, we've got lots of time left. So please, if you have any questions, try and add them in the chat. Otherwise, I'll try and think of some off the top of my head. So, so you talked quite a bit about the, as well as the predator-prey, right? You've got this infection kind of application. So I don't know if this is similar to how the actual COVID pandemic was modeled. Have you looked into that much?
Yeah, so how realistic is when applied to the current situation?
Yeah, exactly.
So I had this question at the beginning of the pandemic, to be honest, and it looks like even though it's such a simplistic model, it looks like it fits quite nicely the real data, especially of the first wave, where the we didn't had too many factors. Kind of now the system has become more complicated. There are people that have become infected. Maybe they can be reinfected. People that are vaccinated. So one should add more parameters to model the current situation, for example. But the first waves looked very similar to these curves.
So another thing we could maybe talk about is kind of how this kind of mathematics that you do in your research is related to kind of students here doing undergraduate degrees. So I think you have students doing projects on this problem, right?
So we have suggested projects on that. One is related to epidemics. So in this, and one remark I could say is that it's interesting, and one can play a bit with the parameters. Like this epsilon is actually, one can say, lockdown measures decrease epsilon, and we decrease the interaction between the infected population and the non-infected. So one can play with these parameters or add more parameters, for example. So we have this suggested this project on epidemics, and another one related to the banking system that I said before. So with the bank loan and the deposit, and how we can find stable solutions that benefit everyone.
Yeah. So I think Manuela actually has a similar project where the context is zombies rather than
so in that particular project, we will co-supervise.
Okay.
So yes.
Yeah, I'd like to do that project. Unfortunately, as a member of staff, I can't apply to do that project.
You can
any more questions from the audience? We've got plenty of time. But if there's not, we'll finish, a bit early, and we'll have a bit of a longer break than expected, which is fine. But one thing I'd also like to ask then is, so yesterday I talked a little bit about chaos theory. So do you see kind of chaotic behavior in these systems?
That's a very nice question. In this XY model, there is no chaos because in two variables we do not have a chaos. But if we have a third variable, Z1, so we have the rabbits, foxes, and the carrots, for example, or as I said, with four variables that you can play a bit and you can create your own model in 4 dimensions. Then most probably the system will be chaotic. There are very few the models that are not chaotic, and that's very interesting.
Yeah, exactly. So the actual real systems that we're trying to model would be
definitely chaotic.
Exactly. Yeah. Okay, very, very good. That was a really nice talk and some nice discussion afterwards. We'll kind of hang on for a few minutes to see if there's any questions coming late. But otherwise, we'll finish a little bit early. Okay, so it doesn't look like it. So what we'll do, maybe so we're not just sat here kind of chatting, we'll take us off the screen. But maybe, Helen, if you could stay
I will be here. I can answer
in the lobby. And then if somebody thinks of a question, we can maybe come back on.
Okay, I will be here. Okay,
so
thank you very much, Matt.
Yeah, thank you very much, Helen. Thank you. So
thank you for attending my talk. Thank you, everybody.
What I'll do is I'll put some informative slides on the background about open days and stuff, and we'll just linger in the lobby. And if you have any questions, please, you can still put them in the chat, and we'll come back on and answer if there are any. Okay, so thank you, Helen.
Thank you again.
Hello. Hi.
Hello.
How are you?
Yes, good, thank you. How are you?
Good. Sorry for this. So we are here back with Brittany. She's one of our former students, and very good to have you finally. Can you tell us about you, who you are, what you did, something
Yeah.
very introduction.
That's fine. So yeah, my name's Brittany Halpin. I went to Lincoln Uni to study maths. I graduated in September 2019. So coming up to 2 years. Gosh, that's scary.
Yes, true.
But yeah, so that's me basically.
Good. So this workshop is aimed for people that have to select university and decide what to do after. So how did you decide to study math? Why, if you want?
Yeah, so I took a bit of a different, well, not a different route, but I was sort of classed as a mature student when I came to uni, because I actually took 2 years between doing my A-levels and then going to uni. I think I mainly just chose maths because I really enjoyed it. Like, I really enjoyed it at A-level. I didn't get the predicted grades I was, predicted, which was a bit soul destroying at the time, I'm not going to lie. But then I ended up doing really well in my degree. So it's just, I think, just about going for something that you really love. And I've always known that I've sort of really loved maths. And yeah, I think you will do well, even if you're a bit nervous about doing it. Because I mean, I ended up graduating with a first, so.
yeah, you did very well, very, very well. Probably the step on the first year was quite difficult, but how your expectation of university match with what you really had?
Yeah. So I think because I took that 2 year gap, I was sort of a bit more knowledgeable about how university would work and stuff. And my older sister went to uni, so I sort of really already knew what to expect. But I didn't also think we'd have as much time as what we did. So I know maths is quite a heavy course. So in first year, you're sort of a bit like, oh, we're in like quite often compared to everyone else. But then by the time you get to third year, you're sort of a bit like, oh, well, we've been coming in and doing this since day one. So it's not really that much of a jump. Whereas I think with some other courses, it was a bit like they were in third year and they were like, whoa, like this is a big step up. But even saying that, so obviously because I'd got the time management down, in third year, I ended up joining a sports team. I still went on like loads of nights out. I went on tour with lacrosse, and like I still managed to get all my work done and like really succeed. So I think it does really help you with the time management and stuff. So yeah, I don't know. I definitely think we had more time than what we thought we had at uni. So to complete work and stuff like that. So yeah.
Good. So what was the most interesting part of your degree or your favorite modules?
Yeah. So I feel like I quite enjoyed it all, to be honest. Some modules, not so much. But I think as it got along more, it was more like the interest, like in maths. It wasn't just because I feel like when you're at school, it's pretty much you're learning maths to pass exams, and you can't really get into the deeper stuff. Whereas when you go to uni, you really see like what maths is about. I think in third year though, my favourite module probably would have been when we had the guest speakers. I can't think what the modules actually.
Advanced topic and instrument.
That's it. Yeah. So in third year, there's a module where we have guest speakers come in, and then we sort of write a review of what we've learned. And they'll come from all different backgrounds, different job roles and stuff. And that was just really interesting because it was actually a chance for us to see maths in the real world. And I don't think you quite appreciate that before you go to uni. But yeah, I just enjoyed it all, really.
Okay, good. I think also your group of friends was quite important on the final. I know that. So what are you doing now? What is that you're doing? I know that you're doing a lot of things like in the third year. So let me.
So yeah, after I was at Lincoln, while I was there actually, I applied to complete my PGCE, which is basically your teacher training to do maths. So I applied for the University of Cambridge. I ended up getting in. I ended up intermitting my year though, just because of the lockdown and stuff like that. So I've just actually recently graduated about two and a bit weeks ago. So I've just finished. Yeah, thank you. So yeah, I've just finished, and now I'm a fully qualified maths teacher. So yeah, that's really exciting, and I have actually got a job for September as well. I've moved to Norfolk now, so I've got a job down here.
Oh, nice. Very good. I'm very good that you're doing good. And so I know that you already said us, but what about what you suggest if someone has a particular difficulty to pick their subject, as choosing what kind of degree they want to pick now?
I think just really look at what degrees are out there, because there are like so many different ones. So I originally actually wanted to do maths and psychology as a joint degree, just because I was a bit worried that my maths wasn't as up to scratch, just because I took that 2-year gap. But then the more I looked into it, I thought that's going to be quite a bit of a challenge, and it is actually more the maths that I want to do. But when I was talking to people, most people were like, maths and psychology, can you even do that? And some unis do offer it. So I would definitely, I think when choosing the degree, just make sure you've really thought about what you want to do. And there's no rush. Like I took 2 years out, and I went through loads of different options of what I wanted to do. I was like, no, I'll just do psychology. I wanted to do engineering at one point. But I think because I took that break, and then I actually thought, yeah, I really want to do maths. And then obviously I came for the open day at Lincoln, and I thought, yeah, this is the place.
Okay, good. Very good. Yeah, we actually you have math and philosophy and physical philosophy as well. So yes, you're right. There are a lot of more options. Okay. Okay. So thank you for your interview. Thank you for attend to this workshop, and
yeah, no worries. It's been good to see you as well. So for anyone listening, Manuela was my tutor through uni. So yeah, I've not seen her since I graduated, which is crazy.
Yeah.
But yeah.
Okay. Thank you. Bye bye. Maybe we have a chat separately.
Yeah,
Bye.
definitely. It's been lovely to see you. Thank you, Manuela.
Bye bye.
Bye.
Hello. So we're back after that short break. I'm here with Fabien Paillasson, who is a senior lecturer in the School of Maths and Physics. He teaches statistical mechanics in third year on the physics program. So hello, Fabien.
Hello everyone.
How are you?
I'm alright, thanks.
So what we're going to do, you've pre-recorded your video, so we're just going to play it as we've done for a lot of the others. And those of you watching, if you could put your questions in the chat, either during the talk or you can wait till afterwards. We'll hopefully have plenty of time again for questions. So as usual, it will just take me a minute to find the video. Okay, here we go. So yeah, please enjoy and we'll speak to you afterwards.
Hello everyone, I'm Dr. Fabien Paillasson, and in this presentation we are going to talk about Buffon's needles. And the goal here is to see the crossing between empirical and formal mathematics. So without any further ado, we are going to start the presentation. Hello everyone, so today we are going to do a bit of empirical math. So what do I call empirical mathematics? Well, to do what I call empirical math, we are going to need a pen here, and here we are at my house, and luckily I've got laminated floor and I've got regular spacing between the wooden planks. Now I'm going to use, for example, this pen, and the actual experiment I'm going to do is simply do something like this and drop it on the floor. Now, what I need to do at that stage is simply record with a 0 if there is no crossing of this particular line, or a 1 if basically it crosses that line. So in this particular case, this is crossing the line, and therefore I can say that this is a number 1 I should put on this. Now, in principle, what we need to do is to actually repeat this experiment something like at least 1,000 times, and take the ratio, or at least do something with the ratio of the number of times we get to 1 and the total number of times we actually dropped the actual pen. Now, what I do in this particular instance is that it turns out these are my kids' colored pen, and I've got more of them. So I've got a bunch of them like this. So what you could do is essentially do the same. So you, instead of doing, one experiment, let's say 20 times or whatnot, you take 20 pens and then you drop them like this. Usually it's much more fun. And then actually you need to care to count these intersections. So for example, here we've got 1, and then here we've got a second one, the red, and then so 3, then 4, then we've got here, we've got a 5 with the blue one. And there is a special rule, which is that there is obviously in my floor, there are edges, right? And the only pens that I can look at are actually the bulk pens. So that's the one that are not touching any edges. So I'm removing from my initial batch the number of pens that are essentially touching the edges, because they have been influenced by the edges. So if I count the number of intersections, and I record the number of crossings, and then I also count the number of bulk pens, color pens, then I can record basically and do things much faster. So instead of 1,000 experiments, maybe I just need to do about 100 or 200, depending on the number of pens you start from. So that's the experiment which I'm going to run, and I'm going to show, the outcome of that experiment if I repeat it many, many times. Right, so let's summarize a little bit what this experiment is about. So we first need to drop pens or needles, whatever you have at your disposal. This can be toothpicks, this can be chopsticks, whatever, of a given length L. For this experiment to work, and what is coming to come as well to work, you need the length of these needles or pens or whatever you use to be smaller
than the spacing between the lines that you are looking like about the crossing. And so the spacing here is called D. So the length of the needles or pens is L, and the spacing between the lines on the floor or on a tabletop experiment that you would have to be D. Now, once we have got this, then we drop them and we count the number of crossings between the pens and the lines on the floor. And we take care of counting only the ones that are not touching the edges for the whole calculations that is coming in a minute. And then we repeat many times this experiment and we try to do something with the data. I'm going, in fact, to show you just in a moment what we do with it. So here is at the bottom is a small portion of the data I've got, and I'm just going to go through some of the items to tell you what they represent. So here on the left-hand side, this is going to be the number of bulk pens. So these are the ones that are not touching the edges when I've dropped the pens on the floor. And so in particular, this number 14 is going to be fed into the total number of pens that essentially were in the bulk and crossing or not crossing with some lines that are on the floor. And so this variable is called n bulk. Now, likewise, we've got the number of intersections. So that's the number of intersections between pens and the lines. And so this number here is going to be n intersect. Now again, this number of intersections is amongst the pens that are not touching the edges. And finally, we've got this particular part here, which is a normalized inverse frequency. So what the hell does that mean? Well, this is a quite maybe cumbersome looking formula, which I'm going to call X, and which is 2 times L over D, so the ratio of the length of the pen divided by the spacing between the lines on the floor. And then this is multiplied by the ratio of the total number of bulk pens that have been dropped on the floor over the number of pens that are intersecting with the lines, and again the number of pens amongst the bulk ones. Now in this particular instance, this is a trial number 1, therefore I've only dropped the pens once, and so I got this particular number, and here I get basically the ratio 14/6 here. Now in case you want to redo this experiment or rework out the particular formula I'm using, the L for me is 15.6 centimeters and D is equal to 19 centimeters. Okay, just in case you want to retrieve some of these numbers by yourself. Now, of course, if you do it at home later on, and I'm going to encourage you to do so, then of course L and D are going to be different. Now, let's have a look at what happens when we move to, let's say, do the experiment a second time. So this is going to change the total number of bulk pens that we can discuss. So this is going to be 14 plus 17. And the number of intersection that I can count is therefore the sum of the number of intersection that have been observed in each of the experiments. So the first one and the second one. So it's 6 plus 8. And in the end, the variable x is going to be 2 times L over D times 14 plus 17 over 6 plus 8. So I hope now that this is relatively clear how this is going to work. And now what I want to do is essentially show you the data that I've collected in my Excel file, and then what is the kind of value I got for x as I continue doing the experiment over and over again. So here we finished with 130 repetitions of the experiment. Now it actually takes a bit of time to do this 130 times, but this is, or maybe this is worth it. So here we obtain in the end this particular number for x, so 3.14 and then 5991236. By the way, here I'm simply just getting out the number given by Excel. Of course, you would also do something maybe more carefully using significant digits and so on. For the time being, I just stick with this particular outcome. Now, this formula, I mean, the formula that gets into it is basically x, 2 times again L over D, and then times the sum of all the total number of bulk pens, so again pens that are not touching the edges once they are on the floor, and then over the number of observed crossings between pens, between one of these pens and the lines. Now in total here it means that we've got 130 terms to be added together, and then the ratio of these kind of additions. So this is a number we obtain. Let's keep this in a corner of our heads and then move on to a different way to approach the problem. And this different way is what I call a formal mathematics perspective. So what is formal mathematics here? Well, essentially the goal is to propose a mathematical model that somehow is going to represent the real experiment that I've made in my living room. Okay, so you can think of it as a game where you've got some objects which are mathematical objects, and you are going to need to describe the space that can be explored by these objects, and then you are going to introduce whatever other quantities and objects that you need in order to model the particular things that you recorded or that you extracted from the data. So in this particular instance, the part of the mathematical objects that we want to look at is basically here I've drawn 2 lines. Obviously here I need to draw at least 2 lines to show the spacing D between the lines, and in blue I've got something representing a needle. Now of course this could be a pen or anything else that simply looks like a stick. Now this is of length L, and again the spacing between the red lines is actually D. Now what we can look at here is the space that can be explored by this particular needle or pen in this characterization, and in particular it shouldn't be redundant. So we try to look at the smallest amount of configuration space, which is not something that is going to be a repetition of something else. So let's look at how this may look like. So here we notice that if I draw a dotted line just in the middle, at the, let's say, midline in between the 2 red lines, I've got essentially a distance d over 2 between the dotted line or the dashed line and the red line. Okay, so there is some form of symmetry between the two. If the needle is within the gray area or within the white area, essentially the two are going to be equivalent. So what I can look at here is focus myself on the gray area that I've put here. Now when it comes to the position of the needle, of course I can characterize the position of the needle simply by looking at its center, or any other point, to be honest, would work for the position itself, except that, as we are going to see in a moment, rotation of the needle is possible too. So because rotation usually occurs about the center of the object you're looking at, center of mass, then it's more sensible to take the center here to characterize the position of the needle. Now, in this particular instance, essentially the needle can move anywhere in this gray region, the x direction, if you will, is not going to matter much. So the horizontal direction here is not going to matter much because it does not influence crossing of the red line. So we are not going to care about it. The y direction, however, which I'm going to mention or call altitude in some of the coming slides, matters, right? Because it tells us essentially where there is possibility to cross with the red line. So once we have this, then we can say that the value y for the position of the needle, so again that's the center of the needle, can take any value between 0 and d/2 if I set the origin of the y-axis to be in the dashed line. Alright, so that's for the first manner to express one of the, if you will, degrees of freedom of this particular needle. Now coming back just here for clarity, I'm coming back at the center here, and one of the things that can happen obviously is that the needle or pen can rotate, and as it rotates then you can measure the corresponding angle theta between the horizontal line and one of the ends of your pen. So that's kind of it. And in this particular instance, you see that the angle theta, again, not to be redundant, is going to be between 0 and pi. Now, one way we can then formalize this graphically is by representing the space or set of all possible configurations graphically, and that's what I'm doing here. And essentially this is every single point in this beige rectangle. So you see on the y-axis you've got it goes from 0 to d/2, so this is the interval we mentioned earlier, and likewise for the theta axis then it goes from 0 to pi. So once we have this, then we can try to create the new object, and that's the final one that we are going to need, which has to do with a subset of the configuration space. So this is here, I've got a subset I, y of the interval 0 d/2, and I've got a subset I theta of the interval 0 pi. And the Cartesian product between the two gives you the subset of all these things, where every single point in that red rectangle corresponds to some configuration of your needle. Now, what I want to look at here is a probability that I call P for a given for the needle to be in the configuration, in one of the configurations in that set, okay, in that rectangle, red rectangle set. So the thing is that probability of a set for being in a particular set is an object, is a mathematical object. And in fact, that's a mathematical object which we are going to be interested in this particular formal mathematics perspective. Now, as in, let's say, video games, once you have an object, you actually need to have rules on how this object is going to behave, and essentially, the rules that characterize that object. When it comes to probabilities, they are characterized, classically at least, by what are called the Kolmogorov axioms of probability. Now, it turns out that although this sounds kind of fancy, and maybe it is, there are only 3 of them, and essentially here I'm going to refer to them as rules. So the rule number 1 is that probability, here is the probability of this subset, the right rectangle, has to be a real number between 0 and 1. So that's the first rule. The second rule is that the probability for the needle to be in any one of the possible configuration, so that's the probability of the entire beige rectangle, is necessarily equal to 1, right? Because a needle cannot be in an impossible or non-existing configuration. It has to be in either one of these configurations. And finally, the third rule involves a second set, which is not overlapping with the first one. And here that I'm taking as being the Cartesian product of an interval I y prime and I theta prime, and that I draw in blue. And the third rule says that the probability for the needle configuration to belong either to the red set or to the blue one is equal to the sum of the probability for the needle configuration to belong to the red set plus the probability for the needle configuration to belong to the blue set. And that's it. This is basically here laid in not even half a page. This is like the whole of probability theory. Now, once we have this, what we can do is try to provide a model. As you can see, from these particular rules, there is nothing we can calculate. So we need to provide a probability model in order to, for example, use rule number 3 to try to figure out some new probabilities and so on. So the model we are going to use here is a so-called uniform probability model. What it says is that under these equally likely outcomes, we've got that it's as if we were sampling a point at random in this rectangle, so that the probability to sample one point is the same as to sample any other point in that rectangle. So there is no region of that rectangle which is favored compared to another one. Now, mathematically, the way to write this down is as follows. If you take a subset of this beige rectangle, so again the red rectangle here, then it says that the probability of that red rectangle, or at least for the configuration to belong to that red rectangle, is equal to a constant c times the area of that rectangle. So you see, it's incredibly convenient because we can relate probabilities to geometric quantities like areas, volumes, etc. Now, the important bit here is that the constant c is independent on the subset I choose. So if I had chosen the blue subset from earlier, the constant c would have been the same. We are going to see that this is going to be important later on. So that's a probability model that we are going to use. And what we want to find out now is, because we need to relate it to the empirical mathematics experiment we've done earlier, which has to do with crossing of pens with lines. So what we want to find out here is that if I've got my needle here with an angle theta, and somehow I fix this angle theta, I want to find out what is the configuration that is going to lead to a crossing. So if theta is fixed, the only free variable I can change is essentially y. So I'm going to leave this up. I put a bit more than the first possible crossing just so that it's kind of visible to you, but in principle I should have stopped as soon as the needle touched the actual red line. Now I'm going to call this particular altitude where the first instance of crossing occurs y min, and this is a function of theta. Okay, so this is going to depend on obviously the value of theta, and any y value above that y min is going to lead to a further intersection of the needle with the line, okay, with the red line. So that's really great. Here we've got a way to quantify for now this thing, which is if y is larger than y min, then this is going to work out. Okay, so once we have this, we can try to write out the equation for y min. So again, remember, y min is the value of y such that the tip, really the tip of the needle, is touching for the first time the actual red line. So the equation for it is y mean is equal to d over 2 minus L over 2 sine theta. Okay, one way to look at this is basically to tell you that the y coordinate of the black spot here is on the one hand d over 2, because it's on the red line, so it's obviously d over 2, but it can also be written as y mean plus L over 2 sine theta by definition of y mean. So now what we get in the end is that because any y larger than y mean is going to be a crossing configuration, then for any value of theta, I can simply plot the region that's in yellow, the region which is corresponding to a crossing configuration. So in practice, because I want to know the probability for a crossing to occur, then it means that I need to know the probability P of this area in yellow. Okay, so the probability again for one of the needle configuration to belong to that yellow area. Now remember what we had said earlier, that the probability for this is going to be a constant times the area of that yellow domain. But what is interesting as well is that the probability for basically the configuration to be any of the possible configurations is also equal to C, so the same constant times the area for times the area of the beige rectangle. Now what we can do from there is simply take the ratio between these two equations, and you can see that we are getting rid of the C's, so that's really nice. So we are getting here that the ratio of the probability for the configuration to be in the yellow area, which is about crossing configuration, over the probability for basically anything to occur, any of the possible outcomes to occur, is equal to the ratio of the corresponding areas. But that's where this becomes a smart trick, because if you remember, when we looked at the Kolmogorov axioms, the axiom number 2 states that the probability of this beige rectangle is equal to 1. So in the end, we get that the probability for a configuration to be in this yellow domain is equal to the ratio of the corresponding areas, so its area over the area of the beige rectangle. So we are almost there, but we need somehow to find a way to calculate the area of this yellow domain. So the way I'm going to do it here is as follows. I'm going to say that the area of the beige rectangle is of course equal to the area of the yellow domain plus the area of its negative part. So if you will, the complementary part of the yellow domain that is going to form the beige rectangle when put together. So if I do that, I can actually get, when I replace in the above equation, that the probability for being in the yellow domain is 1 minus the area, the ratio of the area for being in the complementary domain, beige domain, over the total area of the beige rectangle. Now the difficult part here could be if you do not know how to calculate the area under a curve. So I remind you that we actually know the equation for the curve that is drawn in red here. This is simply y mean, so this is essentially y is equal to d over 2 minus L over 2 sine theta. Now the way to calculate this, if you have seen this or not yet, is related to what is called the fundamental theorem of calculus. And it says that the area of this region is the integral from 0 to pi of d over 2 minus L over 2 sine theta d theta. Okay, now whether you know how to do this or not, if you want me to give some details of it, I would be happy to do it during the questions, but I'm simply going to give you the outcome of this right now. This is a quite simple integral to evaluate. And you would find something like this. So this is d times pi over 2 minus L. Now, substituting back before substituting anything, I need to calculate the area of the rectangle. And luckily, a rectangle area is quite easy to evaluate. This is simply the width times the length. And so this is d over 2 and then times pi, and we're done. So then we can substitute back into the above equation, and we get that this is 1 minus, and then there is parenthesis, 1 minus 2L over pi d. Putting all of this then back together, we get that this is the probability for a needle configuration to be in the crossing configuration is therefore 2L over pi d. Okay, and that's the main result we can get within formal mathematics perspective, so some kind of game with rules and some ways of modeling the pen and the crossing condition. So let's summarize a bit what we have seen so far. So we've got on the one hand the empirical mathematics part, where we performed a bunch of experiments and we recorded them and evaluated the following quantity, which is 2 times L over D times n bulk over n intersection. And we obtained, after 130 experiments, the value 3.1459912336. Okay? Again, here I'm not using any significant digit thing, so there would be something to be said on top of it here. Now, in formal mathematics, we have looked at something a bit more abstract. We have looked at a quantity called the probability, and we have looked at the probability for a needle expressed as an infinitely thin object with very sharp kind of boundaries and so on of a certain length, L, and what are the chances for it to actually cross, given that all possible configurations are equally likely. Okay, so that's a very important kind of consideration. So here we found that the probability for a crossing to occur, given this kind of equally likely thing, which I'm calling here a uniform, is 2L over pi d. I can put it in a form similar to what we have on the left, by saying that we could get actually pi, the number pi, as being 2 times L over D times 1 over P crossing, given this uniform assumption. Now, the pi is a number in formal mathematics, and this number is actually defined in very different manners that enable people to obtain essentially formal estimates and exact estimates of the digits of pi. And in particular, if we stop at the 9th decimal, these are the exact digits for pi. So this is 3.141592653. So we see here that with the two different things we've done, we actually got on the left, in fact, something that looks like an estimate of pi, which is actually in agreement with what we've got on the right, up to the 2 first decimals. Now we see that, of course, what we were doing, in a sense, is not necessarily estimating pi. Obviously, that was kind of the idea. But the bridge is not in terms of pi. The bridge between the empirical and formal mathematics is basically in these two middle formulas. It's basically telling us that we can, in fact, infer from this at least approximate agreement between the two sides, between the empirical and formal mathematics, we can suggest that the ratio of the number of intersection of the number of pens that have been put on the floor without touching the edges is approximately the same as the probability for a crossing to occur under the assumption that all outcomes are equally likely. And that's the interesting bit. That's how you basically make the connection between something which is due to empirical mathematics and something on the right-hand side which is purely formal and in some sense coming outside of a game. Now this particular let's say experiment was proposed by Georges Louis Leclerc de Buffon in 1733. And this is this gentleman. Well, he was much younger when he proposed it. He was, I think, about like in his 20s. And the thing is that he actually proposed it because he directly postulated this particular connection, that a way to evaluate this formal quantity, which is a probability, under the uniform hypothesis would actually be to simply do some experiment in real life. And his objective was in fact to propose an experiment that you could do in real life to get various estimates of pi through essentially random operations. So in case you would want to see a bit further, that's kind of the first time people were suggesting some what is so-called Monte Carlo experiments in real life in order to estimate some kind of abstract number, which is here pi, which, as you may know, has infinitely many digits with no repeating sequences. Right, so this is basically the end of this presentation. I hope this would have inspired you to maybe try out this particular experiment. Maybe you would get a better precision than the one I got, or a better agreement with some of the digits of pi than the one I got. And maybe this enabled you as well to observe that there is different ways of looking at mathematics. And we've got, on the one hand, experiments that are done in some sense in the real world, and then we've got some formal, very well-defined things, and then we need to find a way to match them together, or at least to say that they are approximately going to be equal to each other. So on this, I leave you, and if you've got any questions, I would be happy to answer them.
Thank you, Fabian. That was fantastic. Just get rid of the okay, so yeah, really good. So we've got no questions yet from the chat, but please do put your questions in. So Ben says, love the dedication of doing it 130 times. I just wonder how long it actually took you to do that.
Well, I mean, initially I actually did it more, so in total I probably did it almost 300 times, but initially there were problems with the experiment, so I had to basically there was some trial and error, and yeah, so it took definitely 4 or 5 hours in total. So I used that actually to play with my kids as well.
Yeah,
so they liked it for a couple of hours, but then after that they were bored.
Yeah. So we've got a question from Dylan. How would you decide how many repeats of the experiment to do if you wanted, for example, 2 decimal places of accuracy? So could you, I guess, predict, given your desired accuracy, how many experiments you would have to do before doing them? It's a good question.
So yeah, that's a good question. So again, if you take like the purely let's say empirical math aspect, I think either you can't predict. So if you take really a purely empirical math, so I'm doing the experiment, I'm crunching the numbers, and I'm getting this number out of it, I think that either you need to say I can't predict because I need to do the experiment, or you try to find kind of some kind of sequence. But you need to know somehow what you are trying to target, right? So you need to find to plot the data and try to increase the length of your data, so the number of throws, of drops of your needles and so on, and then see how it appears to converge to some kind of value. And then this can give you, let's say, if you increase by 100, for example, or if you multiply by 10, let's say. So by multiplying by 10, so let's say from 100 to 1,000 iterations, then you can try to see by how much closer you got to the value you seem to be converging to. So that's how empirically you would do it. That's how you would do it in physics. If you want to check how you seem to be converging experimentally towards something, then you would, at least I would do it like this. Now, if you assume that formal mathematics has something to say about your experiment, then there is a way as well to get this part, how this trend is going to go. And this is called assuming each pen is independent of the each other pen.
Yeah.
They are, pairwise independent. Then you can actually use a so-called weak law of large numbers, which says that essentially as you that you are getting closer and closer to the wanted value with a power law, which is 1 to the square root of the number of experiments you've done, or the number of pens you've dropped. So that would be 1 over. Yes. Anyway, so that's kind of how you could do it. Okay. So if you have, if you want to ask more, I'm happy to reply afterwards.
Yeah. So there's there's another question in between, but I'll come back to that one. But Steve says, because it's kind of related, could the experiment be simulated by a program to get a better and better approximation of pi?
Yes. So when I mentioned Monte Carlo simulation, that's actually how they are usually made. So you've got a model, a probabilistic model, so a formal model within mathematics, and then we use, in some sense, actually an empirical model within a computer, which uses actually pseudo random generators. So these are deterministic sequences which give some kind of pseudo random numbers out of them. And then that's what is used in a computer, and that's what is used then to do some numerical experiments, for example, of this needle thing. And I think that probably if you Google it, you would probably find various Java, I can't run Java anymore, applets in my browser, but or Python realizations of these numerical experiments. So that would be a way. Yeah.
So before the next question, I'll just kind of tell you that Fabien is the program leader for maths and philosophy and physics and philosophy, right?
Yeah.
So this question is, do you think maths exists externally to the universe?
Yeah, okay. Well, I don't know. So, externally to the universe. So I'm not quite sure what that would mean, externally to it. So I guess the question is, at least one question would be, well, if we didn't exist, would math exist, right? So at least that's something maybe that is slightly simpler, not as maybe as deep as the initial question, but let's say that's already a tough enough question, right? If we didn't exist, would math exist? So would the mathematics, as we describe it, exist? I don't think so, because at least I don't think so, because I think that it's related to our cognition and various things that have to do with the history of our civilizations and so on. But then if the question is, would patterns exist in the universe if we didn't exist? Then I think that yes. And then if we define mathematics in some kind of broad sense as being about patterns in nature, even if some of them are approximate patterns in some sense, then I would say yes. And then, but okay, so that's how I would, let's say, in 1 minute answer this very deep question, which probably would necessitate a few books.
Yeah, exactly. Yeah. Okay, so we've got a couple of minutes left. If there's more questions, please do put them in. Otherwise, I was going to ask, so this formal derivation you've done, right, seems to depend on your choice of going from 0 to pi. Would it still work if we chose 180 degrees instead?
Yes. So if you remember, the pi, the final pi that in the final formula comes from the area of the rectangle. The width is d/2, and the length is actually pi, because I've chosen to say that the angle was going from 0 to pi. Now, of course, especially coming from A level or from, let's say, high school level or secondary school, people are not usually trained or used to express angles in this, with pi as a reference. So usually they would say 180 degrees instead. And so you could ask, oh, would that still work? And the point here has to be, well, no, definitely if you use 180 as a number instead of pi, it doesn't work. However, in mathematics, in mathematics, as far as at least I will boldly claim, we use numbers. We don't use kind of other things. And the natural numbers, I mean, the natural kind of ways of expressing angles within mathematics is pi is basically pi as a reference, which is expressing radians. Okay. Now, why do I say that? Well, because then you can try to understand what 180 degrees means in mathematics. So 180 degrees actually is the degree part. You need to express it in radians. So the definition of a degree is actually pi over 180.
Yeah.
Right. And so 180 degrees is 180 times pi over 180. Okay, so that's it. Now, of course, you could say, but that's weird. That's tautological. You're kind of tricking us. But think of it, right? A degree is pi over 180. Let's say in mathematics. So then you say, well, what about 90 degrees? Well, 90 degrees is 90 times pi over 180 degrees, and so that's actually pi over 2. Okay, so that's how it works. And so if you adopt this particular convention, then the derivation is obviously independent of the kind of unit you use to actually do the derivation.
Okay, so just finally, I think we've got a minute or so left. The same person who asked the question about the maths existing externally, since kind of followed up and asked, so is that like saying if we didn't exist, a cow would exist, but the way we describe the cow wouldn't exist?
Yeah.
So basically the word cow wouldn't exist, right?
Yeah, I mean, to be honest, you could say the concept of cow maybe wouldn't exist, right? It's always the thing about whether tables exist and so on. Well, if you see a chair, we think of it, or a couch, we think of it as something to sit on, but maybe some people will want to do something else with it if they have never actually sat on a couch. So here it's a little bit like this. If a mosquito is roaming around a cow, do they see a cow as we see it? Do they experience it as we do? Probably not. So that's kind of it, right? So at least that's how I would phrase it. Again, it's not like, I mean, I've thought about it, but maybe not enough to have any super definitive claim to make about this.
Yeah. But it's interesting to think about for sure. Okay, so with that, what we're going to do now is thank Fabien. So that was really good, Fabien. Thank you. And
Thank you.
We've got another student interview just before lunch, and then we'll have an hour break. I'll leave the stream running, but then I'll put up some kind of slides and stuff, and we'll be back at 1 o'clock. So I'll play this video. So cheers, Fabien.
Thank you. Bye.
There we go. Okay.
Today we are here, we have as a special guest Sophie. She's a former student for our degree maths. And I don't know, Sophie, do you like to tell us something about you, what you do,
Yeah, no problem. I graduated from the maths program in 2019, and now I work with Siemens as a graduate engineer. So starting my career off in the engineering industry, specifically within transport and railway. It's been really exciting so far, and yeah.
Nice. As you know, this event is mostly for students that are deciding to go to university. So one thing that probably they struggle with, how to decide to study a particular degree, how to decide what to do for the future. So what were the motivation that bring you to decide for maths?
For me, it was kind of a mix of things, really. One of which is that I really enjoyed it at A level, and I found it challenging. It was definitely a challenging subject for me at A level, and I put in a lot of work to kind of achieve my A level, but I was kind of really wanting to see what maths looked like as a degree subject, what degree level maths was, and how kind of I could extend my A level knowledge into that realm, I guess. So in terms of like the content and that kind of stuff, I was quite excited by that. And I was definitely up for the challenge as well. I knew it was going to be difficult.
So I just so you can tell us how essentially studying at university compare with your expectation. Then can you tell
Yeah,
us?
in a way, I found the kind of, if we're talking about university and the content of the course and things like that, I found A level maths to be kind of a more difficult jump between GCSE and A level than between A level and degree level. So within the first year, there was a lot of kind of small extensions to topics that we'd done at A level, but nothing too dramatic or drastic. And that was kind of a really nice way to get me used to how to study at degree level and how to complete assignments and kind of what to expect from lectures and workshops and things like that.
Okay. And what was the most interesting part of your degree? I don't know.
I think overall my favourite part of my degree was actually my final year project. So it was completely different to anything that I'd ever done before. It was a pure maths project about symmetries of infinite structures, and I absolutely loved just being able to do it at my own pace and kind of with my supervisor kind of researching into something so abstract and difficult that I could have just, when I started my degree, I wouldn't have been able to imagine myself completing something like that. So it was the feeling of kind of being in control of the project and completing it, how amazing that felt. Just knowing that was all my hard work. Yeah, it was my favourite.
Yeah, I can understand this. So some kind of, would you recommend studying at University of Lincoln or?
Yeah, definitely. Just for a multitude of reasons, really. I mean, on the maths program itself, I loved how varied the degree was in that we were learning kind of pure maths concepts and applied maths, and then also kind of some programming and that kind of thing, which is really good for going into industry. So I now work, well, when I finish my grad scheme in August, I'll become a software engineer at Siemens. So that's kind of a bit of a direct link to that. I hadn't done any programming before I went to uni, and I kind of am really happy with how that has turned out, and that was all due to the programming that we did in the first couple of years of the degree.
So essentially you cover also the last question that was what you're doing now.
Yeah, so I've been on a 2-year grad scheme with Siemens. So it started off as a rotational grad scheme. So I was doing like 3 to 4 months with different placements within the business. And that was really good because you get to see a little bit of what everybody is doing. And that gives you a really good idea of kind of project life cycles and kind of how things all work and how you might want to slot into those things in the future, I guess. Okay. So I always sort of knew that I would like to do something that directly felt like problem solving to me, and definitely with the programming, I knew that I could sit there all day and be like, okay, I've got this problem, I need to solve it. What do I need to do? And that was really appealing to me. So when it got to kind of most of the way through my grad scheme, I just started saying to people, look, I really like this problem solving, doing software and programming, and that is kind of where I'm working now. And then when I officially finish the grad scheme at the start of August, I'll become a software engineer officially. So it's really exciting. Yeah,
it looks like it. Congratulations then. I'm very happy that you can use our skills in an effective way. Okay. Do you have any suggestion, I don't know, about particular suggestion to give eventually for someone that is particularly doesn't know what kind of path or what kind of degree can get after A levels and I don't know.
Yeah, I mean, I'd kind of just say that if you have enjoyed something before, then that's not going to change just because you're studying it at degree level. as I was kind of alluding to before, it gently leads you into the first year. So it won't be kind of something to panic about. If you've enjoyed the content of an A level, you will enjoy it at degree level. That's completely what I kind of found between my A level maths and my degree level maths.
Okay, thank you very much. It's
Thank you
been
so
very
much.
nice. Thank you for participating in this interview. So hopefully see you soon.
See you soon. Thank you so much.
Yeah. So Sophie, if you happen to be watching, thank you very much. That was great. I wasn't going to come back on, but I forgot to say something at the end of Fabienne's session. So he's recently started a series on YouTube called Not So Fast. So the idea is to address some maybe misconceptions that students tend to come to university with. So what I'm going to do is just put a link to Fabienne's channel. I mean, I'm sure you can find it by yourself, but just so it's easy, I'll put a link here. And it's definitely worth checking out some of his not so fast videos. So I think there's 5 so far, but there's new ones every week or so. So I just forgot to mention that. Okay, so enjoy your lunch, and I'll see you back here in around an hour. Hello, welcome back from the lunch break. I hope you're all okay. I'm now joined by Anita Tillai Sundaram, who is a lecturer here in maths. Hi, Anita.
Hi, everyone. Hi, Matt.
So Anita is an algebraist. She teaches things like complex analysis and tensor analysis. But today she's going to talk about fractals, which is a very fascinating subject. So I think you're doing the talk live, right, Anita?
Yes.
So do you want to prepare your slides and then you kind of can start when you're ready? So just before Anita starts, let me just remind you to please put your comments in the chat on YouTube and we'll see them. And we'll hopefully have some time at the end for some questions. So over to you, Anita.
Thank you, Matt. So I hope I'm in full screen. So hi, everyone. Good afternoon. So yeah, before I go into any detail concerning all the words on my title, let me say a little bit about what my research is about. And so my research, as Matt hinted at, is in algebra, and specifically it's in this area called group theory. So this is one topic in pure mathematics. And what is group theory? So group theory is the study of symmetries. And this is actually a very old subject. So it dates back. So yeah, group theory is the study of symmetries. And what is a group? So group theory is the study of groups. And a group in pure mathematics is just a collection of symmetries. Okay, what exactly do I mean by a collection of symmetries? So we'll look at an example shortly. But let me just say that group theory is actually quite an old subject. So it dates back to the time of the ancient Greeks. However, when they studied group theory back then, they studied it in quite a concrete form, whereas nowadays group theory is studied more in an abstract form. Again, what do I mean by that? We'll have a look at an example in a bit. So, but yes, so the ancient Greeks, when I say they studied group theory in a very concrete form, so the group and the group theory that they did was that they studied symmetries of shapes, such as a square, a cube, a tetrahedron, dodecahedron. So here I've got not a very good picture, but so for example, what the ancient Greeks studied, and that was an early form of group theory, were the collection of rotations of a cube, for example. So your collection of rotations of a cube, that is an example of a group. Some of you probably might know about group theory, so this is then nothing new to you. But yes, you can consider the symmetries of a tetrahedron. That is an example of a group. So what do I mean by when I said that group theorists nowadays mostly study groups in an abstract manner? So what is this sort of process of abstraction that I'm going on about? So for example, so what lots of group theorists do nowadays is, so take for example, the rotations of a cube, symmetries of a cube. So that is a group. So when I say that we often, group theorists nowadays study groups abstractly, we, in some sense, forget about the cube and we just study our symmetries, our rotations as abstract symmetries. So we kind of throw away the object that our group is acting on, and we just study the group in its own right. So this is kind of an example of what we call the process of abstraction. And it may sound a little scary, but it's actually not so bad, this sort of process of abstracting out sort of the underlying essence of what you're looking at. And it's a very useful tool because it allows you to go further in mathematics and then apply your mathematics to other areas of science. Yes, but as I said, this abstraction process, it can sound a little scary. So let me actually give you a simple example to illustrate that maybe at the beginning it sounds scary, but you just need to give yourself time to get used to this abstract way of thinking, and then it kind of becomes second nature. So the example I want to give you is if you think about the quantity 2. Okay, so we're all happy with the quantity 2, for example, or take 3 if you like. But if you go back in time, so say thousands of years before, mankind wasn't too happy with just thinking about this quantity 2 as an abstract quantity. It always had to be 2 something, like 2 apples, 2 people, 2 oranges. If you just say 2, they'll ask you like 2 what? So they weren't so, back in time, people weren't so happy just thinking of abstract quantities, which is something that's no problem for us nowadays. So this is one example of how what often happens in mathematics. We have this, we sort of abstract our concept and take it further. And yeah, one needs a bit of time to get used to this sort of process of abstraction. But with this example too, you can see already, you've already experienced how powerful it is to have an abstract quantity 2, because then you can divide by 2, you can take to the exponent 2, you can take to the logarithm to the base 2, you can do all kinds of things. But if you're kind of tied down to always thinking of 2 as in terms of 2 apples, what does it even mean to divide by 2 apples and that kind of stuff? So this is just a simple example of roughly what group theory is like today. We deal with abstract groups or symmetries. Okay, so that's a little bit about what I do. And now linking back to the title of my talk, so I mentioned Hausdorff dimension was one of the first words in the title of my talk. And so within the study of group theory, the study of groups, there's so many things a mathematician can look at. There's so many things you can study about groups. So a group, as I said, is a collection of symmetries, and more often than not, it's a collection of abstract symmetries, but not linked with an object. And there are lots of things. There are really so many different directions you can investigate. For instance, one is to look at sort of what we call, so a group is an algebraic structure. One thing one could look into is you could study a group's maximal substructures, and this is quite a big topic and it's got quite a lot of important applications. So that's one of the things you can do. And so one of the things that I do in terms of groups is to study what's called Hausdorff dimension in group theory. So, but before I link Hausdorff dimension with groups, let me actually tell you a bit about what Hausdorff dimension is and when it came about and how it was used when Hausdorff dimension was first defined. So as the name implies, it's some kind of dimension. And so we all have an intuitive idea of integer dimension. So something of dimension 1 is like a line, something of dimension 2, a 2-dimensional object is a square, a 3-dimensional object is a cube, and so on. So we have an intuitive concept of integer dimension. So what Hausdorff dimension is a generalization of our usual intuitive concept of integer dimension to non-integer dimensions. So a Hausdorff dimension allows us to consider objects that have dimension 0.45, for example, or dimension 1.32. So everything in between an integer, a non-negative integer, we can speak about an object which has that dimension, and this is called the Hausdorff dimension. Okay, it's this concept of Hausdorff dimension. It's not the only generalization of our usual concept of integer dimension. There are other kinds of dimensions out there, like the Minkowski dimension, the box dimension. But let's just keep to the Hausdorff dimension. Otherwise, things will get a little complicated. So this was first invented. This concept of Hausdorff dimension was first invented in the 1930s, so about 100 years ago, and so towards the end of my talk, I'm going to bring in those two concepts, Hausdorff dimension and group theory, together. But when Hausdorff dimension was defined in the 30s, it was defined in terms of shapes in nature, or what we call fractals. So a classic example is a snowflake. And so that's when the context in which Hausdorff dimension was used back in the 1930s when it was introduced. So oh, sorry, my nose is running. So with what is a fractal? So I said a classic example is a snowflake. So let me just put a picture up. And so a fractal, as you can see in the snowflake, is a shape that's somewhat irregular. So in terms of the snowflake, it's quite spiky. And so a fractal is an irregular shape that no matter how often you zoom in to parts of your shape, it retains its irregularity. It looks just as the original shape did, but it's just you just zoomed in. So specifically with the snowflake, it's quite spiky. And if you zoom in on one of the spikes, you still see lots of small spikes. And if you zoom in on that tiny spike, you still again see all the spiky crystal structures. And so yeah, if you keep on zooming in after your snowflake, you kind of see little snowflakes. So that's an example of fractal. Another nice example is this kind of broccoli here, which you can see that if you pick, if you pick one of, I don't know if you can see my mouse, but if you can pick one of your broccoli heads, and you can see it's made up of kind of little heads of broccoli, and if you zoom in on one of your little heads, it looks just like your original big head of broccoli. And if you can keep on zooming in, you still see kind of like just the same sort of broccoli head formation, just smaller. So these are examples of fractals in nature. So that's where Hausdorff dimension first came about. It was used to kind of classify these different fractals by assigning, working out their Hausdorff dimension. And so, for example, broccoli, I believe the Hausdorff dimension is about 2.3, that sort of range. So what does actually the Hausdorff dimension tell you about your shape that you are studying? So what does it tell you about your snowflake or your broccoli? So as I said at the beginning, the Hausdorff dimension is a generalization of our usual concept of integer dimension. And so something of dimension of Hausdorff dimension 1 roughly kind of behaves like a line, takes up as much space as a line would do, whereas something of Hausdorff dimension 2 behaves like a two-dimensional object, of course, and it will have an area. So it takes the sort of the space that it takes up in our world, you can sort of quantify that in terms of the area. So a two-dimensional object has area, a one-dimensional object has no area. So if you have, say the snowflake probably has this picture of a snowflake probably has Hausdorff dimension about 1.3, say. And so having Hausdorff dimension strictly greater than 1, but less than 2, is telling you that this object in some sense takes up more space than a smooth line, but because it has Hausdorff dimension strictly less than 2, it has no area. So it kind of has properties between that of a line, but not as much as sort of a square, if that makes sense. Okay, so this is where Hausdorff dimension kind of came about. It was first used in the study of fractals in the 1930s and 1940s. And one of Hausdorff dimension's sort of claim to fame is that it was used to solve the coastline paradox. So a paradox is sort of a phenomenon that seems counterintuitive. It sort of seems to be giving you a contradiction. So that's what you mean by a paradox. And what is the coastline paradox? So the coastline paradox is the phenomenon that when you try and measure the coastline, so say the coastline of Britain, when you try and measure the coastline of Britain, and the more accurate you try and make your measurement to be, the longer your coastline seems to become. So it seems to, your coastline seems to just blow up. It just keeps blowing up to infinity. And so this is a bit of a counterintuitive phenomenon, because you would expect that the more precise your measuring instrument or your technique for measuring the coastline becomes, you would think you would sort of zoom in onto the true length of the coastline. And this indeed happens if you're dealing with a so-called nice object. So we'll look at an example in a short while where if we apply the same sort of process of making our measurement more accurate to, say, a giant circle of diameter 1,000 kilometers, then you see there that this process will zoom in onto the true value of the circumference of your circle. But with a coastline, this didn't happen. So this is the coastline paradox. Okay, let me be a bit more specific by when I say that your measuring instrument becomes more accurate. And also let me give you some figures to illustrate how much longer your coastline becomes when your measuring instrument becomes more accurate. So let's have a look at some figures. But before we do that, let me just say, show you on the next slide what exactly, how does one go about measuring the coastline or approximating the length of your coastline? How does one go about doing that? So actually the method of approximating a coastline, so say the coastline of Britain, generally it was quite a primitive way of approximating the length, but it does the job. So how do we approximate the length of the coastline? So as you can see here, say let's look at the leftmost picture, you would approximate the length of your coastline with sort of via a series of straight lines. So you kind of approximate your shape with a bunch of straight lines, and you just add, and then your approximation of your length of your coastline is just the sum of all these straight line distances. So on the far left, we've got quite a rough approximation where, say, I've just taken points along the coast that are, say, 500 kilometers apart, and I just join up the dots and measure the straight line distances. So we're good at measuring straight line distances, so that's quite easy. And you just add up all the lengths of your straight lines, and that's an approximation. Maybe not the best approximation of your coastline, but it's an approximation. And then if you move on to the middle picture, you see our approximation has got better. So in other words, that's what we mean by the measuring instrument becoming more accurate. So in the middle picture, say we have taken points that are about 200 kilometers apart along the coast as the crow flies, and we just added up the distances, the lengths of each of these straight lines, and that's hopefully giving us a better approximation of the coastline as opposed to the left picture. And then on the far right, we've got an even better approximation where, say, our points are, say, 50 kilometers apart. Right, so this is how you would approximate the length of a large irregular object shape. So, okay, now let's look at some figures. So with the left approximation, what would be then the length of the coastline? And with the middle approximation, what length would we get? So we can see how the differences in our approximation, how are they changing? Okay, so this is a table with the lengths on the right column, and the left column is, so I say compass setting, and this is the distances between the points that you've picked along your coast. So if I say compass setting 500 kilometers, that kind of is akin to the leftmost picture, which was a very rough approximation where we've just picked points kind of 500 kilometers apart on the coastline. Anyway, so that first approximation is giving us the length of the coastline being about 2,600, okay? And sort of the middle picture on the previous slide, where we've improved our approximation by taking points along the coast that are 100 kilometers apart. So here we've got a bit of a jump as compared to the first approximation, but never mind. So here we've got 3,800 for the length of our coastline. And then if you keep improving your compass setting, so even 17 kilometers apart is quite a good approximation. But you see with the lengths here on the right-hand side, it doesn't seem to be zooming in or on one value. It doesn't seem to be converging to one length. It's kind of it just keeps getting longer and longer and longer. So this is the coastline paradox. So why does the length keep going? Why does the length keep growing? And before I bring in the solution kind of brought in by House of Dimension, let's have a look at what happens if you were to consider, instead of, if you compare what's happening here to a nice shape. So if you were to take, say, a huge circle of diameter 1,000 kilometers and go through the same process of approximating your circle and looking at the lengths that you get for each approximation, you will see here a different behavior for the circle. So I've got a table and a similar table, and you can see on the right-hand side that the circumference of your circle, so the length of the outline of your shape, it is converging to the true value of your circumference. Because, okay, so on the left again, when the compass setting says 500, then you've picked points along the circumference of your circle that are 500 kilometers apart as the crow flies. And so there the circumference is going to be 3,000, okay, which is reasonably far off from the true value of the circumference of your circle, which is 1,000 times pi. But then you see after already 4 iterations of improving your approximation, you've basically hit the true value here. And you can see also in the previous 2 approximations, you're getting closer and closer to the true value. So this is kind of what you would expect when you would do the same approximation for your coastline. But why did it not happen here? Okay, so why this is not the case is because we've made the mistake in this process of approximating our coastline as a series of sort of summing up sort of straight line distances. So the mistake that we have made here is we have treated the coastline like a smooth, straight line. The way a circle, the circumference of a circle, the outline of a circle is a nice, smooth, straight line. Whereas the coastline is actually an example of a fractal because it's an irregular. It's not. Well, the coastline of Britain is not given by a nice, smooth, straight line because if you zoom in on, say, the coast of Lincolnshire, it's squiggly, like any other coastline. And if you say zoom into the coastline of Skegness, say, is just as squiggly. And the closer you get, it still remains squiggly because you can see then all the pebbles. And then if you go even closer, you've got all the sand particles. So it doesn't behave, it's not a smooth line. It's a squiggly line, so what we say formally a fractal. And that's why the length is blowing up, because it shouldn't be here. It's not a smooth straight line. So that's why this approximation technique is not going to give us a true value, because being the squiggly fractal, it's taking up more space than a line. Okay, let's be specific. So on the next page, let me kind of put down a few points about how the House of Dimension solved the coastline paradox. So in 1967, so this came a few years after the House of Dimension concept was introduced, Mandelbrot showed that the House of Dimension of a coastline, so not specifically the coastline of Britain, but any coastline, the House of Dimension is strictly between 1 and 2. And this establishes that it doesn't behave like a smooth line. So in other words, it's in a regular shape, or specifically a fractal. And as I was mentioning earlier, that the House of Dimension of a shape tells us what sort of properties and characteristics our shape has. And so the House of Dimension of the coastline being strictly between 1 and 2 is telling us that a coastline takes up more space than a line. But because its House of Dimension is strictly less than 2, it has no area still. So it's somehow in between a line and a square. So, and because now the House of Dimension is telling us of the coastline is strictly greater than 1, and it says essentially, loosely speaking, that a coastline takes up more space than a line. So in other words, it doesn't make sense to measure its length. And so because it would just have length infinity. So that's why in the coastline paradox, the better your approximation became, the length of your coastline is just kind of blowing up to infinity. If this is a bit vague, why the length of a coastline is going to sort of approach infinity, let me give you a very simple example. So any object that has House of Dimension strictly greater than 1 will have this property that its length is going to go to infinity. So let's take a nice concrete example. So if we take a square that has House of Dimension 2, because we know it just has normal dimension 2. So if we try and measure the length of a square, what are we going to get? So if you want to measure the length of a square, and of course this is a filled-in square, not just the outline of a square. If you want to measure a filled-in square, so when I say I want to measure the length of a square, you want to measure how much one-dimensional space your square is taking up. Okay, so if we follow the approximation method that we saw, you would approximate your square with several little lines. So sorry, I can't really draw this out for you, but if you imagine your square, you kind of fill it in with horizontal lines. And what you want to do is then sum up the length of all these horizontal lines. So if you imagine a square, say a 1 by 1 square, you would fill it in with lines of length 1, and you need infinitely many horizontal lines to fill in your square, of course. And so therefore the length of your square is going to be infinity. So this is kind of roughly what's going on with the coastline when you try and measure its length, because it doesn't behave like a one-dimensional object. So that's kind of what's gone wrong with the coastline paradox. Oh, excuse me. And so with this knowledge that a coastline actually doesn't behave like our standard smooth square, we now know, now this information is telling us that yes, if we want to go and measure a length of a coastline, we just need to specify with our length that we get what sort of level of approximation we use. So then it's fine if someone else got a different length because they measured it differently, as long as they specify how they measured the coastline. It's okay. We now know it's okay to get different lengths. So that's fine because we understand how a coastline behaves. But you can imagine going back like a few hundred centuries when people didn't realize that a coastline doesn't behave like your standard smooth line. This could have led to sort of military disputes when someone claimed that their coastline, or two different important people, I suppose, tried to compute the length of a given coastline or border between two countries, and they each got different lengths, and you can imagine one would claim the other was lying or something, and that could lead to some problems in the past. It probably did as well. But right now, with the knowledge of Hausdorff dimension, we now understand that the length of your coastline just depends on how we're measuring it. So that's kind of the problem solved there. So a coastline, of course, I am saying that it is a fractal, and also the examples that I gave of the snowflake and of broccoli, of certain kinds of broccoli, and also the other trees that we say are fractals. But actually, these fractals are well, approximate fractals in nature. So the definition of a fractal, which I mentioned briefly, is that no matter how much you zoom in, it always looks like the original irregular shape. But with examples that I gave you in nature, like snowflakes and the coastline or broccoli, nature is such that you can't keep on doing something to infinity. So with a snowflake, for example, a real snowflake, you could maybe zoom in 4 times and then it just sort of flattens out. Same with the coastline, you kind of zoom in maybe 5, 6 times and then it will flatten out. So if you want to find an example of a true fractal, in the sense that if you keep on zooming into infinity, it still looks like the original shape, you have to go into mathematics to construct true fractals, is what we say. So now we're going to look at some examples of mathematical fractals, and these really are examples that no matter how you keep on how many times you keep on zooming in, nothing's going to flatten out. But in nature, you can't find examples like this. Okay, so that's what we're going to look at now. So just quickly, let's revisit the definition of fractal. So formally, a fractal is a shape or curve that repeats itself at any scale on which it is examined. So no matter how many times you zoom in, it still retains it looks like its original picture, the original shape with all the jagged bits and stuff. And in case you're interested where the name comes from, it comes from Latin, the word fractus, which means broken or uneven. So in other words, irregular. It's an irregular shape. Okay, so now let's have a look at 2 examples of mathematical fractals. So here we do have these, the zoom in, you can zoom in to infinity and it will still look exactly as the original shape. However, as you can imagine, because your mathematical fractal, your true fractal, is should have the property that no matter how many times you zoom in, it still looks like the original object. That's going to be difficult to draw. And in particular, I can't give you the final picture of the fractal in one picture. So what I can do, and what one usually does with mathematical fractals, you kind of depict the process you would have to go through in order to construct the mathematical fractal. So in other words, I give you the recipe for constructing this mathematical fractal, and the recipe says just do this step over and over and over and over again. And at the end of the day, after infinitely many steps, out comes the fractal. Okay, but maybe that sounds a little complicated, but let's look at an example where actually the step that you have to do is quite clear and quite straightforward. Okay, so the first example of a mathematical fractal that we're going to look at is what's called the Cantor set. It's named after mathematician George Cantor. Okay, so the picture that I'm going to put up next may look a little overwhelming. I'm not very good at pictures, sorry. so what you're going to see is sort of a series of lines, sort of horizontal lines. And what you want to look at is look at the top layer, because the second layer depicts what you need to do to the top layer to get to the second layer. And the third layer is what you do to the second layer to get to the third layer. And so in essence, the layer is kind of showing you how eventually how your set is changing, your shape is changing. And if you sort of keep on looking down the layers, eventually you kind of get to the Cantor set. Okay, let me put the picture up. Maybe then it's a bit easier to understand. Okay, so you want to start looking at the top. So how you construct the Cantor set. So you want to think of this as a number line. So so the top line is a line of length 1. And what you might want to imagine thinking of it as a number line. Here the left point is the number 0 and the rightmost point is the number 1. So your line represents all the numbers from 0 to 1. So everything with decimal points, as long as you're between 0 and 1 and including 0 and 1, this is the top line. And so at the end of the day, the Cantor set is just going to be a collection of disjoint numbers. But okay, let's start at the top. So we're starting, so the recipe for constructing our Cantor set is we start with this line of length 1. And then looking at the second level, it's a bit of spotting the difference here. What have we done to the top line to get to the second level? Well, we've removed the middle third of our interval of our line. Okay, so to get to the second level, we've got then the first segment, the left segment of our line of length 1, so it's just 0 to 1/3, and then we've got the rightmost segment of our line, so from 2/3 all the way to the number 1. Okay, so to get from the first line to the second stage, second level, we've removed the middle third. Okay, so this removing the middle third for our unbroken line segment is the step that we need to keep on repeating to infinity. Okay, so if you look at then the second level, which consists of 2 lines of length 1/3, and now for each of them, you remove the middle third, and you see here you get left with 2 segments, each of length 1/9. And likewise with this rightmost segment at the second level, you again remove its middle third. Okay, and then you keep on doing this. So in other words, whenever you have a continuous line segment, you attack it and you take out the middle third. And you keep on doing that. So you see here, we've taken out the middle third, and then this guy here, the segment of length 1/27, we again take out its middle third, and you keep on doing this. You keep on doing this to infinity, and at the end of the day, you will be left with just a scattering of points, and this collection of points forms the Cantor set. Okay, so what kind of points will remain after you keep removing the middle third? So for instance, the point 0 here, if you again look at the very top layer, the leftmost point, I kind of said, you can think of it as the number 0, and the rightmost one is the number 1. If you're thinking of this as lines along the number line. So the point 0, you can see if you look down each layer, it survives. So the number 0, no matter how often you remove middle thirds of your unbroken lines, you will never remove 0. So the number 0 will be in your Cantor set. So that's one number in your Cantor set. And likewise, the number 1, you can see as you go through this process of removing the middle third every time, your number one will survive. And likewise here. On the second level, if you look at the number 1/3, likewise, that's going to survive. Oops, sorry. Likewise, that's going to survive. So that's great. It's another example of a number that will be in your Cantor set. So yeah, so you can actually write down mathematically all the numbers that are in the Cantor set, but let's not go into that. Okay, so this is an example. So I hope I've given you an idea of how you would construct a mathematical fractal. And how do we see that this is a fractal? So because at the end of the day, this set is just a bunch of disjoint points at the end of numbers. But so one way to see that this is a fractal, so remember the fractal is a shape that when you zoom in, it looks like the original picture. Okay, so with this Cantor set, if you look at this, so I know this is not this picture is not the Cantor set, but it's kind of how you go about constructing the Cantor set. But you can just take it. If you want to look for the symmetries within the Cantor set, you can still just consider this picture here. So for instance, if you look at this picture as a whole, and of course you want to imagine this process, all these layers going on to infinity. So you have, I've only drawn the first 5 layers, but it kind of goes on. Anyway, if you look at this whole picture, and then if you look at this, the left part here, which starts with this segment of length 1/3, if you look just from that part all the way down to infinity, so this sort of left section from the second level onwards, it looks just like the original picture, doesn't it? So this whole left bit here looks like your original picture here, with the one starting with this line segment of length 1. So this left bit here, starting from the second level onwards, is identical to the original picture. I just scaled it down by 1/3. So there you see, if you kind of zoom in to the left bit, it looks exactly like the original picture that we have in front of us. It's just reduced by a factor 3. And likewise, you could go also to the right segment of your picture here, the right part from level 2 onwards. And likewise, this picture here is identical to the original picture that we have here, only it's scaled down by a factor 3. Right, so this is kind of hopefully giving you an indication that it is a fractal, because no matter kind of which bits of the picture you zoom into, so say even this bit here, everything here, it will look identical to the original picture here. It's just sort of shrunk by a factor 1/27 or so. Okay, so this is an example of a fractal, a mathematical fractal. What is this house of dimension? So unfortunately, I haven't got time to sort of walk you through how you would calculate the house of dimension of this fractal. It's not too difficult. This is something you could do as a second-year undergraduate in mathematics. So it's not difficult, it's doable, but there's just some terminology I would need to introduce. So never mind how the actual details about computing the house of dimension. I can kind of roughly give you an idea how you would compute the house of dimension. So let me just tell you what the house of dimension of the Cantor set is. And this is on the next page. So the house of dimension of this Cantor set that we saw is log 2 over log 3. So hopefully some of you are familiar with log. You can take it also to any base, log to the base 10 if you like, log to the base e if you've heard of that, but it doesn't matter. If you're not familiar with log, let me just tell you that this number is strictly between 0 and 1. So it's strictly less than 1, but it's strictly greater than 0. And remember, a line has got house of dimension 1, and just a single point, a single dot on its own has house of dimension 0. And 2 disjoint dots, of course, will have house of dimension 0. And any finite number of disjoint dots will have house of dimension 0, because a dot just has dimension 0. So this fact here that the Cantor set, which the Cantor set is just a collection of dots, but the fact that is you have so many dots that it doesn't behave like a finite set of dots in terms of dimension. So the fact that the house of dimension of our Cantor set is strictly greater than 0 is telling us that, yes, our Cantor set we know is just a collection of dots, but there are just so many dots, and that it takes up more space than just a finite amount of dots. So it has dimensions strictly greater than 0, where just if you only had sort of a sparse collection of dots, the house of dimension would still be 0. Yes, so this house of dimension being strictly greater than 0 is telling us that the Cantor set doesn't behave like our usual collection of dots, so to speak. And the house of dimension being strictly less than 1, because log 2 over log 3 is about 0.67 or so. The fact that it has house of dimension strictly less than 1 says that it has no length. So the length of our Cantor set is 0. So there's no point computing the length. So that's telling us, yeah, that we shouldn't bother trying to compute the length. Okay, so unfortunately, I said I couldn't really walk you through the steps and how you compute the house of dimensions of your Cantor set, but let me give you a hint as to how do you end up with log 2 over 3. So the 2 and the 3 are the important numbers to remember. Let me go back to the picture that we had. So where is this 2 and 3 coming from, which then gives you log 2 over log 3, is the fact that this sort of symmetry that we have here in this picture. So what I mentioned earlier as well, that if you look at this left part of the picture from the second layer onwards, it's a scaled down version of the whole picture by a factor 3, scaled down by a factor 3. And likewise, the left part, sorry, my left and right confused, the right part of this picture from level 2 onwards, again, is a scaled down picture of the whole thing by a factor 3. So you've got kind of both the left and right parts, so that's 2 parts, and they're both scaled down by a factor 3. So that's kind of where the 2 and the 3 are coming in, because it's scaled down by a factor 3, and you've got these 2 parts that both are scaled down by a factor 3. So that's kind of roughly how you get log 2 over log 3. Okay, just another quick example. So this example is called the Koch snowflake. Again, it's named after mathematician Koch. And again, as in the previous example, because it's a mathematical fractal that no matter how often you zoom in, it will look the same. It's difficult to sort of give you the picture of the fractal in one go. We're going to do the same thing as with the Cantor set. We're going to go through how would you construct the Koch snowflake. So here I've just put in 3 steps. So again, you want to look at the top layer and then compare that to what you do to get to the second layer, and what do you do to the second layer to get to the third layer. So the top, you kind of start the same way as we did for the Cantor set. You start with just a line segment of length 1. Okay, that's the top line. And then what do we do to this line segment of length 1 to get to the middle layer? So what we've done is actually, so it's difficult, I haven't put any measurements in here, but what goes on is you remove the middle third of your top line, your straight line segment, you remove the middle third, and then you add a hat. Okay, so you've removed the middle third, and then you add a hat. So with the Cantor set, you just remove the middle third, and that's it. But here you've removed the middle third, and you add a little hat to where the hole is. And the thing about this hat is that the length of this left segment here on the second level, which is a third, is the same as the 2 slopes of our hat. So this slope here has length a third, this right slope here has length a third, and this one here has length a third. So in other words, when you put your hat in, your 4 little bits of line segments need to have the same length. Okay, so what is the step that we keep repeating to infinity? This is the step is whenever you see a straight line segment, so this is a straight line segment, or this is a straight line segment, you attack it and you take out the middle third and you put a hat at the middle third. Okay, so that's what's happened to the third step. So you see, if you look at the left horizontal straight line segment, you've removed the middle third and you added a hat. And if you look at the left sloping line segment, you've removed the middle third and added a hat. And likewise for the right one, you've removed the middle third and added a hat. So so this, you keep on doing this to infinity. This is will give you the fractal called the Koch snowflake. And you might ask yourself, okay, why is it called the Koch snowflake? It doesn't look like a snowflake. Well, maybe it does look like a snowflake to you, but actually what one does, oh yeah, sorry, this is where I put in a few more iterations. So you hopefully it looks more like a side of a snowflake, because it's kind of the spiky sort of jaggedness that a snowflake has. But to kind of really see clearly that why it's called a snowflake is because you, instead of starting with just 1 line segment, you can start with 3 line segments put into the form of a triangle. And with each of these sides, you do the whole remove middle third, add a hat. So you see here the removed middle third is in green. So here, if you look at the next iteration and the one after, it looks more like a snowflake, hopefully now. So that's kind of how you would get the Koch snowflake. And here, the house of dimension of a Koch snowflake is log 4 over log 3. So this is again a number which is strictly greater than 1, but strictly less than 2. So this is saying that a Koch snowflake, again, if it's a bit like a cosine, if you want to measure the length of the outline of your Koch snowflake, the length is just going to go to infinity. But because the Hausdorff dimension is strictly less than 2, the Koch snowflake still has no area. So it's not a 2-dimensional object, but it takes up more space in our world than a standard 1-dimensional object. So that's kind of what Hausdorff dimension is telling us. So again, a little hint, where is this 4 over 3 coming from? So here you've got 1 line segment, and here you've got 4 line segments, and they've been scaled down by a factor 3. So that's kind of where the 4 over 3 is coming from. So just to end, I did say at the beginning that I work in group theory, and actually one of the things I research on is Hausdorff dimensions in group. So I'm not going to talk about this slide at all, other than just to give you an idea of what kind of my result could look like. So this is from one of my papers where we've looked into a group that had lots of Hausdorff dimensions when you look at substructure. So this is kind of what we had. So just so you have an idea, if you've never seen a maths paper before, this is just a part from a maths paper. But yeah, maths is a bit like a language. So it's you have to first unlearn the terms before you can understand what's going on, unfortunately. But yeah, so I think I've taken enough time. So thank you very much. Sorry, Matt, I think you're still muted.
Sorry, yes.
Should I stop sharing?
I've taken the slides off, that's okay.
Okay, cool.
So, yeah, sorry, I was just kind of rambling there. So Luigi asks, does every fractal, it's a 2-part question, does every fractal have a non-integer Hausdorff dimension? Also, what is the Hausdorff dimension of the Mandelbrot set?
The first question, those are really good questions. Thank you. The first question, no, you can have a fractal, and I think you can construct fractals similar to the Cantor set, something called Cantor dust, where you could give it an integer. You could construct it such that you have an integer dimension. So yeah, that's possible. Okay. And the second question, oh, I should know. You're obviously more knowledgeable than I am if you know about the Mandelbrot set.
Well, I don't know this for sure, but I think the fact that those 2 questions were asked together implies that it is integer. Maybe.
Oh, okay.
I don't know though. For some reason I'm thinking 2, but I don't know if that's. I don't know what.
That would be good detective work, Matt. I think that's probably you're probably right.
I think I've got 2 in my head, but I don't know if I'm correct on that.
Yes. So sorry. Mostly I work with Hausdorff dimensions in groups. So I'm not. I learned about fractals a while ago, and I think they're really cool. But I don't usually work. Study fractals. I'm not so up to date.
So there's another one from Luigi. Kind of asks: is there a unit of measurement for dimension 0, like there is length for 1D, area for 2D? And then Ben, afterwards, kind of, there's a bit of discussion going on in the chat. Ben said, I guess it's just a binary kind of existence or not.
So I guess you're asking for, so the word length is what you would use for measuring how much space a 1-dimensional object takes. So you're asking what's the word for length for a 0-dimensional object.
Exactly, yeah.
We don't really have a word for that in our usual sort of English setting, because it doesn't take up space, I guess. But for the case of an object which has got non-integer Hausdorff dimension, you would, so the all-encompassing term for length, the analogy for length and area and volume for non-integer dimensional objects, you would just say you would use, say, a little s for the dimension. So if it's s for a half, whatever, the s Hausdorff measure. So that's the kind of, so s can be any number.
So it's
So
really
if S is
abstract.
pi, yeah. So if it's S is pi, so you've got a fractal of dimension pi, it would be the pi Hausdorff measure. So one Hausdorff measure is just what we call length. A 2 Hausdorff measure is what we call area. And something like a 0.5 Hausdorff measure, we don't have another name for that. So we just call it a 0.5 Hausdorff measure.
Okay, there's we've got. I mean, we're over, but this is interesting. So we'll kind of answer a couple of more. Somebody asks, I don't know if I missed it, but what are the modern day uses for fractals?
Okay, so I'm not such an expert, but one example that I read somewhere is say, so arteries are one example of a fractal. And if you know what the Hausdorff dimension is, so that's telling you sort of how much space, how great the spread of your arteries, the density. And I guess that could help in figuring out how good the transmission of oxygen and that kind of stuff is. So that's one vague example. So with the coastline paradox, for instance, I guess there is just knowledge is power in some sense, and the application is more that we now understand why we've got this discrepancy in the lengths if you measure it differently. And so I guess one vague application would be that it just stops people fighting over the length of the coastline because you now understand it better. Other examples of fractals are, so the galaxies are examples of fractals. I imagine if you know the Hausdorff dimension of your galaxy, that, again, maybe I'm not the best person to ask about that, then probably you could understand the properties of the galaxies a bit better.
I think in material science as well, it comes up quite a lot, like porosity of materials and stuff.
Yes, great. Cool, you probably know better than me.
The last question I wanted to ask is actually the first one we got. I think early on in your talk, you said something about applying mathematics to other areas of science. And I think the fact that you said other areas of science kind of implied that you consider maths a science. And the question is, do you consider maths a science?
Yes, very much so. Yeah, we don't need a lot of equipment generally, especially pure mathematics. But yes, I would definitely say it's still a science. And also one often says that pure mathematics is the queen of all sciences. But yeah, so definitely, yes, I would consider it a science.
Okay, fantastic. Very good. So there's some more questions, but we don't have time for those. We've got we've got 2 students waiting in the lobby for some interview with Manuela. So we'll just thank Anita. So thank you, Anita. That was really interesting.
Thank you very much.
So what I'll do now is, goodbye. What I'll do now is I'll take Anita off and I'll add in I'll add Manuela.
Hello. Bye.
So you're going to interview 2 students whose webcams are currently off, it seems. There we go.
Okay.
So I'll add them in now. I'll disappear. I'll have a little break. And so we're a bit behind schedule by maybe 3 minutes or so. So just kind of go as long as it is natural. Don't feel like you have to rush. And we can start the last talk a little bit late. Okay?
Yeah.
So, thank you.
Hello, hi. We have 2 of our 4th-year students, Stacy and Leslie. Sorry, usually I mix your names, so hopefully I will not do. And today we talking about you. You can introduce yourself. Can you tell us about you, who you are, what you do?
I'll go first.
Yes.
So my name's Stacey. I just finished the 4-year math program. I started on the bachelor's and then in my 2nd year decided to switch over to the master's. So it was just a switch online somewhere, and then I moved over to the master's and just finished it.
Good.
I'm Leslie, so I've also just finished the master's. Unlike Stacey, I did actually start my degree on the master's, but yeah, so we've both just finished and now going on to the next things.
Okay, so now one question about how did you decide to pick math as your degree?
So when I was doing my A-levels, maths was my highest subject at AS, and I spoke to my maths teacher and realised that quite a lot of the stuff that I liked looking at, like academically, was focused on maths. I like looking at the patterns and stuff and finding out why stuff happens, and I feel like that's a really good use of maths, so I decided to do it at uni.
Yeah, I was like a little bit different. So it was one of my best grades at A level, but I really didn't know what I wanted to do after uni. I didn't know what I wanted to do with my future. And out of the options that I was considering, I felt that maths opened the most doors, essentially. It left a lot of things open and I could go into a lot of different fields at the end of it. So that's why I chose maths in the end.
Okay, good, interesting. And how does study math at university compare with your expectation before start?
There's a lot more to maths than what I think I realised. So the maths that you study at university is a lot more broad than what you would study at A level or at GCSE. You go into a lot more detail and you see a lot more uses for maths that you wouldn't have necessarily seen prior to starting uni. So you don't always know about the applications of certain different areas of maths.
Yeah, I didn't really know what to like expect like content wise within the degree, but I definitely enjoyed it. And like just studying at university, I think there was a lot more like support available than I thought there would be. Like we had a lot more contact hours than I expected and stuff like that. So I didn't actually, I felt it was a lot less daunting than I expected it to be.
Okay. And what was the most interesting part of your degree? What, I don't know, module you like more? Or...
So we've just finished our master's dissertations. So it's like a project that we do for the entire second half of our master's year. And you do one in third year as well, but you do that over the course of the year. And I really enjoyed having the opportunity to research heavily into one area and look at one specific topic and choose the direction of what I want to study about that and which direction I want to take it. So I thought that was really good.
I think my favourite part was actually like having guest lectures and stuff like that. So like when we did industrial maths and advanced topics, I liked seeing the applications of where we use the maths and like seeing actually like putting context to the stuff that we'd been studying. I liked that aspect of it, and it really like allowed me to see where I could take this maths in the future and like how useful my degree could be. So I found them lectures the most interesting. I loved that aspect of it.
Okay, yeah. Also, someone else before said that the advanced topic was very interesting. Good to know. And what your plan now that you graduating? Do you have any?
So both me and Leslie sort of have the same plan. We're both doing our initial teacher training to become secondary school maths teachers next year. Throughout the time at uni, I studied pedagogy in my third year, which is something that when I was applying for teaching, they really looked favourably on. They really liked that I'd had some experience talking about what teachers need to know to go forward. So yeah, I'm becoming a maths teacher.
Yeah, as Stacey said, I'm doing exactly the same. I didn't do as much like actual teaching stuff during my degree, but we both did the teaching internship between our like second and third year, I think it was.
Yes.
And yeah, that was like really fun. It was nice to have that.
And that was organised sort of through the school. They advertised it in one of our lectures. So
Yeah, we do. We do advertise. We invite people in. So good. One last question will be: if you can you have some tips or some suggestions to students that are particularly not sure what they want to do in the future, what kind of degree they want to do in the future? Do you have any, I don't know, suggestions? What they can be,
I definitely recommend going to open days because you get to speak to the students that are actually on the course, and you get to find out what they think are the best parts of the course or what they don't quite like or what they think should change. So definitely go to open days because you also get a feel for how the university is, because it's not just the course you're looking at. You also want to be at university. You're going to be there for a couple of years, so you want to be as comfortable as possible. So I definitely recommend going to visit places.
Yeah, I also think if you're not sure like where you want to go or what you want to do, the internet is probably your best friend. There is so many different league tables and websites where students themselves talk about it and stuff like that as well. And like just make sure you're going on lots of different sources to look at the information so it's not biased, and you'll find all universities pretty much list their modules so you can see what they actually offer within their courses and stuff like that, because a maths degree at one university might be completely different to another place, and that's something you should consider when looking at where you're applying to as well. So I just think definitely make sure you're making the most of the resources available to you and look at it like in detail.
Can I ask you one last question? This is a little improvised because I know that you are essentially part of our Math and Physics Society and also very active student ambassador. I don't know, can you tell us a little bit about the social kind of aspect at Lincoln?
So
if you want to.
Yeah. So this year, both me and Leslie were on the committee for the Academic Society. I was president and Leslie was social sec. So that really involves organising socials and events and sort of revision sessions and some little academic support for students in the school. And it looks great on your CV. If that is something you're interested in, definitely recommend getting involved in societies and then being on the committee for one. At the University of Lincoln, I think there's a society for nearly anything you could imagine. And if there's not one for what you want, it is very easy to set one up. I think you need like 5 people to agree, and then you hand it off to the Students' Union, and they say, yeah, okay, have fun.
Yeah.
Plan some events.
I definitely recommend joining societies. Like I've got friends now that I'm friends with purely from joining societies and stuff like that. So it's definitely a great way to make friends. And if you're joining a society, that generally means you're also making friends with people that are into the same stuff as you, which makes it very easy to like organize doing stuff together and whatever. So like it's definitely nice. And I mean, even just get involved in the socials that the school organise as well, because they are so fun. Because like we went to like all the Christmas parties and end of year events and stuff like that, and they were always great. And it's nice to just have that time to relax as outside of your studies as well.
Yeah.
Okay, thank you very much. I just use this occasion to thank you for your support during the last years, and yeah, you did, and see you hopefully next year as alumni. Okay, thank you. Bye.
Thank you.
Yeah, thank you, everyone.
So I can go now.
Yeah, thank you, Manu. Thank you very much. And I'm joined now by Evgeny Kukro. Sorry, we're slightly late, Evgeny. Evgeny is a professor of pure mathematics. He's an expert in algebra and group theory. And he teaches in first year here, he teaches ideas of mathematical proof, plus some other stuff as well. So Evgeny, you're going to talk about group theory, I believe?
Yes, my talk is about group theory, which is part of algebra, and you can say this is algebra of transformations, and it really integrates all parts of mathematics.
So I've just found your video now. I'll play it in a moment. But again, I'll remind you as usual, please put your questions in the comment section, and we'll have some time afterwards, and Evgeny will answer some of your questions. So enjoy.
Here. This lecture is about group theory. Group theory is part of algebra, of modern algebra, and can be characterized as algebra of transformations. In fact, every part of mathematics has its own transformations, important transformations which preserve certain mathematical structures. They can be described as generalized symmetries. Here are some examples. In geometry on the plane, the structure, mathematical structure, means distance. Distance the same as shape of figures. And so you can ask what transformations of the plane preserve this structure, preserve the shape of figures, preserve distance. The answer is well known. Such transformations are either mirror reflections in an axis, or rotations about a point, or parallel translations, or their combinations. These are the transformations preserving the geometrical structure on the plane. Another example is about equations. Consider this equation in 3 unknowns. And by transformations here we mean changes of variables or permutations of these variables. Preserving the structure here means not affecting the equation. You can see that if you replace x1 by x2 and x2 by x3 and x3 by x1, then the first term becomes the second term, the second becomes the third, third becomes the first, so the equation does not change under this change of variable, under this transformation. So this is one of the transformations preserving this structure. But for example, if you simply transpose x1 and x2, leaving x3 intact, then the equation changes, so this is not a transformation that preserves the structure. It's not allowed. And so in every other mathematical object, for example, like a Rubik's Cube, it also has its own symmetries. All collections of elementary particles have their own symmetries in physics, or crystals, or other things in natural sciences, but mainly in mathematics there are their own symmetries which are important, and the study of which is important in those parts of science or parts of mathematics. When we consider all such transformations of a given object which preserve the structure, they form a group. And the word group here has precise mathematical meaning. It's not just any group in common language. This has a precise definition which we shall see a bit later. Here is an example again in geometry. Consider the square ABCD on the plane, and consider transformations of this square which preserve this square as a rigid figure. Such transformations are called isometries. So it's well known that such isometries of the square are rotations or reflections, mirror symmetries. So we can see there are rotations, say counterclockwise about the center through 90 degrees, through 180 degrees, to 170 degrees, which is the same of course as 90 degrees clockwise. And we also include rotation through 0 degrees, which is the identity transformation when nothing is changed. This is important for mathematical purposes. And there are of course reflections. There are reflection in the vertical axis, in the horizontal axis, and in the diagonals. So altogether we have 8 such transformations preserving the square as a rigid figure, and these 8 transformations form the group of isometries of a square. This group has a special symbol. D8 is this group of isometries of the square. In such groups of transformations we introduce operation or multiplication, or in other words group composition. So here multiplication is not the same as multiplication of numbers, it's simply the same word used for this group operation. And this group operation is simply performing one after another. If we have two transformations G and H of some object A, then we simply perform G first and then H after that. So every element in this structure is sent to the image G of A and then to the image H of G of A, like for composite functions. And this can be illustrated by this picture. Here the object A is simply depicted 3 times. It's the same object, just to make it more clear how the composite is, how this operation is formed. First an element is sent by G, then the image is sent by H, the resulting arrow is sending the element under this product G circle H. So this resulting composite transformation is called the product. Sometimes we don't even write this circle, simply G times H, but this is not the ordinary multiplication, it's the product in this sense, the composition of transformations. In some books this is written as H circle G, but we shall stick to this notation G circle H, when G is applied first and then H. It's important that the group of transformations is closed under this multiplication, under this operation of composition. This is fairly obvious because if you apply G, you preserve your structure H, then after that you apply H, the same structure is preserved again, so the composition also preserves this structure. We can say in other words that if we have this group of all transformations preserving A, the group G, then this group is closed under our operation, under this multiplication composition of transformations. If we have two transformations G and H, then the composite transformation G circle H is also in our group G. Let's have again look at the transformation of the square and introduce this notation for anti-clockwise rotation through 90 degrees to be A and reflection in the vertical axis to be B. The question is, what is the composite A circle B, the product AB? We know this result, this product must be again one of these transformations, either reflection or rotation, but which one? To determine what is the result, we simply look at the images of some vertices. Look at where, for example, vertices A and B go under the product. Under A goes to D. When you rotate anti-clockwise, A goes to D. And then reflection in the vertical axis sends D back to A. It means that the product AB sends A to A, to itself. Look at where B goes. Under rotation, B goes to A, then reflection sends A to D, so there is the product AB sends the vertex B to vertex D. So A is sent to itself and B goes to D. Clearly, the only transformation is the reflection in the diagonal AC. A goes to A and B goes to D, so this product must be the reflection in AC. Some other products can be also computed. For example, if you perform A after A, this can be denoted A squared. Again, this is not ordinary powers of numbers, this is simply A circle A. Rotation through 90 degrees, then again 90 degrees gives rotation through 180 degrees. If you perform B squared reflection, then reflection you simply go back, which means you obtain the identity, the transformation which does not move anything. And also, if you perform rotation 4 times through 90 degrees, you send everything back to itself, so A to the 4 is also identity element E. Okay, let's now consider another product. We considered product AB, now consider product BA. If you look at where vertices go, A goes under B to D, reflected, then under rotation D goes to C, so A goes to C under the product BA, and B goes to C first and then under rotation to B, so B goes to B under this product B circle A. And again, this can only be reflection in the diagonal BD when B is fixed and A goes to C. We know the product must be one of those reflections or rotations, so it must be the reflection in BD. And here is an important remark. On the previous slide we saw that the product AB was reflection in AC, but here the product BA is reflection in BD, different. So the product BA is not equal to the product AB. In other words, groups are not commutative. AB is not equal to BA. Unlike ordinary multiplication of numbers, this group multiplication, group operation is not commutative in general. Let's compute another product, A cubed circle B. A cubed is, of course, rotation through 270 degrees anti-clockwise, so A goes to B and then B goes to C under reflection. So A goes to C under this product A cubed B. B goes to C under A cubed and then back to B. So B goes to B under A cubed B. So this is again the same reflection in BD, because B goes to B and A goes to C. So this product A cubed B is reflection in BD. So this is actually the same as product BA. We can note this fact. So BA is not equal to AB, but instead it's equal to A cubed B. And at this point we can actually also mention that products are associative, which will be a useful property. Rather than writing with brackets A circle B and then circle C, it's actually the same as A circle the product B circle C. So we can actually simply write without brackets. This can be seen on this picture. Here the same object A, the same is depicted 4 times to make it clear how these products work. If you have A circle B and then apply C, it's really the same as simply applying first A, then B, then C. And if you do this for the product A circle BC, again you see that this is the product BC, and the resulting product A times product BC is again the same as applying A first, then B, then C, and therefore we have this property of associativity, which simply makes it easier to write these products without brackets. So we now also ditch this notation of circle, because in group theory it's usual to write simply products like products of numbers, but of course these are not numbers but elements of the group. So we simply write AB instead of A circle B and A cubed instead of A circle A circle A. So what we have now for our group of isometries of the square D8, we have 8 elements. These are the rotations. E is the identity transformation or rotation through 0 degrees when nothing is moved. Then we have rotation A squared, A cubed, and these products are reflections. B is reflection in the vertical axis, A squared B is actually reflection in the horizontal axis, and AB and A cubed B are reflections in the diagonals, as we saw on the previous slide. And we saw already that B squared is E, identity transformation, A to the 4 is E, identity transformation, and the product BA is equal to the product A cubed B. That's what we already established. And here is an important moment. We can now forget the square. We now have these relations, these are called relations. We have this list of our elements of the group, and we can simply forget the square and work with these 8 elements using these relations without looking at the square. Everything we want to know, any other product of between these 8 elements, any question about this group can be solved using this information. And this is the moment when an abstract group appears. So this is an abstract group of order 8. It's called the dihedral group of order 8. And it's no longer a group of transformations, just a group as an object in algebra. So here is an example how a calculation can be done using these relations. Suppose we have an equation for x, an unknown element x in this group D8, and we want to solve this equation a times b times x times b is equal to b times a in this group D8. Solving this equation for x is similar to how we solve equations for numbers, but the difference is we must multiply by inverses from a certain side. On the certain side, we simply use these relations. We know that b squared is e, so we can say that b is its own inverse. E is like identity 1. A to the 4 is e, so a inverse can be regarded as a cubed, and we have this relation BA is equal to a cubed b. So to solve this equation we simply multiply by inverses, but important on which side we multiply and in which order. This is important because the group is not commutative. AB is not the same as BA. So what we do, we simply multiply by A inverse first on the left, then by B inverse on the left, and then by B inverse on the right. In this way we obtain x, because when we multiply by A inverse on the left, A inverse A vanishes, it becomes identity. Then by B inverse, B on the left vanishes, and so on. So we obtain this answer for x. But of course we want to represent this in the standard form as one of those elements in the list for D8 as on the previous slide. So we simply transform this product using these relations. So B inverse is the same as B, A inverse is A cubed, and then we simply arrange this BA in the middle to be, by our property, it's A cubed B, so we rewrite BA as A cubed B. Then A to the 3 times A to the 3 is A to the 6, which is A to the squared, because A to the 4 is E. So B squared is also identity element, so it also vanishes because its identity element doesn't change anything. So it becomes simply BA squared. And we can also arrange in the order as in our list to make A's to appear in front. We simply use our relation again. BA is A cubed B, then BA again is A cubed B. As a result, we have A to the 6, which is A squared, times B. So the abstract groups are defined in this definition. So in algebra, a group is actually any set of elements with an operation, which is called multiplication. But of course it's not multiplication, ordinary multiplication by numbers, but the operation on this group. And the axioms which must be satisfied are here. First, the group must be closed under this operation, under this multiplication. If you have two elements, then the product must be in the same set. The operation must be associative. AB times C must be equal to A times BC. There must be an identity or neutral element E, such that E times A is again A, and the same as A times E for all elements in the group. And every element must have an inverse, such that G times G inverse gives you the identity element. In applications, the main example is simply the group of transformations of a certain structure. Some mathematical structure like that square or like the whole plane, simply all one-to-one mappings of the underlying set preserving this structure. The operation on this group of transformations is simply the composition when we perform one after another, and all axioms are then satisfied kind of automatically. We noted that if G and H preserve the structure, then the product preserves the structure, associativity was described, neutral element is simply the identity or mapping when everything is fixed, and the inverse mapping exists, which is also preserving the structure. But group theory in itself studies groups in their own right. When we are not studying groups of transformations, we can study groups themselves, so to speak. And group theory is an important part of modern algebra and is actually a strong point of algebraic research in our Lincoln School of Mathematics and Physics, which was founded not too long ago, in 2014. To give some idea of the kind of results which are obtained in our research, let me repeat that the group is not necessarily commutative, and we said the group is commutative if every elements commute. AB equals to BA. So we saw that not always a group is commutative, and therefore it's of course a very nice property, a very desirable property to have commutativity. So getting more commutativity is a very good type of result. Here is a simple example when the conclusion of this theorem is very strong, when the group is proved to be commutative. Suppose we have a group G in which every element squared is equal to the identity element. G squared is equal to E for every element G. Well, then the group is commutative. So I repeat, this is an example of a very nice result when some property implies this very nice property of being commutative. Well, the proof is not very difficult. We simply consider any two elements AB, write this product AB times AB must be identity element because every element squared is identity, so we have this equation. Now we multiply by A on the left and by B on the right, and use of course associativity. That's what we get. A times AB times AB times B equal to AEB. But of course here we have AA, which is identity, all elements squared are identity. Here BB is also identity. So we have E, B, A, E on the left. And on the right, of course, we have AB. Well, E can be dropped, identity element, so we obtain that BA is equal to AB as required. Well, I can say that many parts of my own research in group theory are about obtaining greater degree of commutativity of the group. Not always a group is proved to be commutative, but may be proved to be close to commutative. And just to give you some idea of how this commutativity or degree of commutativity is measured, I have to introduce another definition, and this is the definition of the commutator. So if we have two elements AB in a group G, then the commutator, denoted by these brackets, this is the special notation in group theory, square brackets AB, is the product A inverse, B inverse, AB. And this element kind of measures non-commutativity of the elements. Actually, this commutator AB is equal to identity element E exactly when these elements AB commute. Well, this is quite a simple property. If you have commuting elements A and B, then of course we can rearrange here A and B like BA. Then in the middle we'll have B inverse B, which is identity element, can be dropped. We obtain A inverse A, so this is again identity element. The whole product, the whole commutator is identity if these elements commute. And the converse is also true. If this commutator is identity element, we can multiply by A on the left and then by B on the left, like this. We obtain BA on the right, and here everything vanishes but AB. So we indeed obtain AB equal BA. If the commutator is trivial, if it's identity, then elements commute. And of course, if all such commutators are identity elements, then all elements commute, and so this is exactly when the whole group is commutative. Well, but not all groups are commutative, and some groups may be non-commutative, but still kind of close to being commutative, to some degree. Some degree of commutativity, and these generalized commutative groups are defined using these commutators. Here is the definition of soluble groups. Soluble groups are defined by using iterated commutators of commutators. For example, if you require that any two commutators commute, so the commutator of any two commutators is identity element, then this is the definition of soluble group of derived length 2. Derived length 1 simply means the group is commutative. So here we kind of iterated this property by taking commutators of commutators. And this can be done to degree derived length k. When you repeat this process, take commutator of two such commutators, you obtain definition of derived length 3, and so on. Iterating this, taking such commutators, we obtain definition of soluble groups of derived length k. Soluble groups, by the way, got their name from solubility of equations by radicals. And this was actually historically one of the theories where group theory first appeared at the beginning of 19th century. Well, Galois theory deals with equations of arbitrary degree, like this, and with every such equation we consider the group of permutations of its roots. So here the transformations are permutations of the roots of the equation, and this group is known as Galois group. So we consider only permutations which do not change the equation. And the theory of the Galois theory here gives the answer that the equation is soluble by radicals exactly when this group, the Galois group, is soluble. I'm not giving the exact definition, but just mentioning this result. And this is why the term soluble group appeared, because this was exactly when the group is soluble by radicals. And in fact, Galois theory gives a complete answer, and in particular produced examples of equations when they are not soluble by radicals. When the group is not soluble, then the equation is not soluble. There are some equations which have non-soluble Galois groups, and here is one such equation, a concrete, very simple equation of degree 5. This equation has non-soluble Galois group, and therefore there is no formula to express the roots of these equations, of this equation by radicals. You may know that up to degree 4 there are formulas. Those famous formulas by Cardano or Tartaglia, Ferrari. There are formulas just like for quadratic equations, for equations of degree 3 and 4, and this is because the corresponding Galois groups are always soluble up to degree 4. But starting from degree 5, there may be non-soluble Galois group, and therefore there is no such formulas starting from degree 5. To get closer to my results, my research in group theory, I need to introduce another definition of groups which are close to commutative, but not commutative in general, when we iterate commutators in a different way. For soluble groups, we considered commutators of commutators, but here we take a commutator of elements x2 and x1, and then commutator with another element x3, and then commutator of the resulting commutator with another element x4. So this is another way of iterating these commutators, and if you write this equation to be equal to identity element for all elements in the group, you have the definition of an nilpotent group of class C. Such nilpotent groups may also be non-commutative, but closer to commutative than soluble groups. And well, with this definition I can already show you some example of very recent paper where results on some limits of finite groups and commutativity type conditions were used to obtain properties which are defined in terms of nilpotency, like in the definition on the previous slide. This is one of the recent papers obtained, published in Journal of Algebra, a joint paper of myself and my collaborator in Brazil. And here is the abstract. You can see that in the definitions these commutators are used to define a certain class of groups, and then the conclusion is that such groups is close to nilpotency, there is a finite normal subgroup such that the quotient is locally nilpotent. Nilpotent is the term which I defined on the previous slide. So this is simply to give you an example of recent research in group theory conducted in Lincoln, where results of greater commutativity were obtained. In general, group theory appears everywhere in mathematics, and in itself it's also developed as in its own right, studies groups, and there are various types of groups. There are many different parts of group theory, and new results and methods appear all the time. As in the whole of mathematics, actually, the more you know, the more is the shoreline between the known and unknown, and the more open problems appear and new methods of study are required to be developed. In many other parts of mathematics, group theory arises in Galois theory, in algebraic topology, algebraic geometry, in the theory of dimension reduction in differential equations, in cryptography, and in many other parts of mathematics. Here are some books on applications of group theory in natural sciences, where groups are used as measures of symmetry, in crystallography, in quantum physics, in material science, and often they are used as a language to describe symmetries of such structures, but also often give insight into the structures, into the corresponding theories in chemistry or physics or crystallography. Groups, like many other algebraic structures, they simply arise as abstractions from various mathematical objects and theories. So once you isolate those properties which are required for groups of transformations to function, you obtain abstract theories which make these theories and objects more transparent, and in this way algebra provides answers and techniques, methods of study, insights in many parts of mathematics and even natural sciences. As one of the great mathematicians said, algebra is generous. She often gives more than is asked for.
Thank you, Evgeny. I forgot my mic was on mute again. Yeah, very interesting talk. I liked that quote at the end there. Yeah. So we've got a few minutes for questions. So there's one from the audience, from Joshua. Says, when you define the identity as the composition of A and B, then sub it in, is that to help achieve a higher commutativity?
I'm not sure what is meant by this question. When you write E is equal to A times B, it simply means that A and B are mutual inverses. And of course, every element commutes with its own inverse. But this is, for free. It's in the axioms. It's not something we prove.
It's not a definition.
But I'm not sure if I answered the question, what was meant by this question. But yes, A and every element commutes with its own inverse, and this can be used for achieving greater commutativity.
And so I was going to ask about this so you talked about this D8 group, and then you talked about this idea of solubility. So if I understand correctly, if D8 is soluble, then it would be derived length 3, correct? Is that
not really.
Okay.
Well, actually, this particular group D8 is derived length 2.
Okay.
But
Okay.
compute the commutator, it will always be a squared, and a squared commutes with everything, so therefore it's actually derived length 2. And in fact, this group is even nilpotent, which is a stronger property, and every nilpotent group is soluble, so this group is even nilpotent. Yes.
Okay. Okay. There's no more questions yet, so I'll continue for a minute or so. So you mentioned applications in physics. So you mentioned crystal structure and particles. And I think one of the books you showed had chemistry in the title.
Yeah.
I was wondering if there's any applications in other sciences, such as biology or...
Yeah, of course, yes. Actually, for example, if you consider DNA sequences in genetics, you can consider substitutions of symbols which are used for encoding DNA sequences. These famous A, T, G, C symbols. And in some papers on genetics, they actually use substitutions or permutations of these symbols. And in this way, group theory appears. Actually, in such situations, group theory often appears simply as a language. It's simply very convenient to use transformations as elements of the group, and quite often not really deep theorems are used, just the language describe the situation. And for example, for classification of crystals, there are famous theorems describing all possible crystals, for example. And there, of course, group theory is used more substantially. You have to really know certain groups. But there are, of course, other applications in physics which are more difficult or more fruitful even, like what I mentioned, the dimension reduction. When you have certain differential equations, you can consider special type of groups, continuous groups of transformations, which preserve those equations. And in case these groups are big, it means that you can kind of reduce the dimension of the problem. You can, instead of considering 5-dimensional problem, you can reduce it to 2-dimensional problem, which is of course much easier to study, even numerically. This is an application of group theory. Ordinary equations solvable by radicals. The same question was about differential equations when they are solvable by integrals in certain sense. And again, the answer was in terms of group theory. You have these groups of continuous transformations, and they can also be solvable or non-solvable, and they are solvable by integrals exactly when these groups are solvable.
Okay.
It's a very nice theory, similar to Galois theory.
Okay. So what, I don't know if there's an easy answer to this question or not, but I wondered why these groups, why this D8 group is called dihedral.
Dihedral, I guess because it's related to the square. I don't know. It must be some Greek word,
right, okay.
Like the hedral must be related to the square.
Okay, okay. So finally, I was just going to ask, you can answer kind of generally or specifically with Lincoln, but where do students kind of see this stuff in a maths degree? Is it quite early on or is it towards the end?
Well, group theory appears even in the advanced A levels, but only as a special module, and it's not always run at schools. But in university courses, group theory often appears only in year 2 or year 3, and in particular in Lincoln we have group theory module in year 3.
Okay. So I think we're kind of over time, so let's finish there. So thank you very much, Evgeny.
Okay.
That was fantastic. Thank you. Sorry, I kind of put him off a bit earlier there. So yeah, we're done now. So thank you everyone who's watched. I'd like to thank all of our speakers, especially Manuela, who's helped me present and who's actually, is actually her idea in the first place to host this. I'm sure we'll do it again next year. So if you have any feedback, we'd be very happy to hear that. So you can email me with some comments. And before I go, I'd just like to kind of remind you Hold on, just give me a second. We have open days this Friday and Saturday. They're virtual open days, so you don't have to actually come to Lincoln. So they're between 10 and 12 on Friday and Saturday. Okay, so we'll end the stream there. So thank you very much, and have a good day.